Professor Sri Ramamurthy Kolkata. So Sri Ramamurthy completed his PhD from IIT Madras in 2009 and joined the Department of Electrical Engineering at IIT Hyderabad. He is currently an associate professor in the same department. His research interests include signal processing, speech analysis, machine learning, and deep learning. He is going to deliver talk on a signal processing view of deep architectures. We are truly delighted with your presence, sir. I request you to take over the session.
Okay, thank you very much. Am I audible now?
Yes, sir. Yes, sir, you are audible.
Okay, thank you. So first of all, I thank the organizers for giving me this opportunity to deliver this talk. Okay. Today I'm going to talk about the signal processing view at deep architectures. Okay, I should first confess that I am not at all related to the autonomous vehicles or cyber physical systems, so I will not be able to give examples from that area. My domain of work is speech signal processing, so my examples may be loaded with speech or to some extent the text. Okay. And coming to the title of the talk, I should say that I am pretty new to the deep neural networks. At one point when I am doing my PhD, I never understood neural networks. In fact, I am so averse to neural networks that even though my supervisor has a textbook on neural networks, I said to my friends that I will not write the word neural network in my thesis. Okay. And I stick to that. In my thesis, I did not use neural networks. It's completely signal processing. So, but last 10 years, there is no way out actually. I have to learn the neural networks, or I have to understand neural networks and start using, because the line between signal processing and machine learning is getting thin day by day. Okay. So with my signal processing background, I started looking at studying the neural networks. Then I just tell you my experience, what I have come across. Okay. So coming to basically, so if we see the signal processing way, okay, we say that because a signal is the one that conveys information. Okay, if something is not conveying information, we do not call this signal. Especially in the case of electrical signals, this information is embedded in the sequence of samples basically. So what is important for signal processing person is the sequence. Okay, the sequence in which the samples are evolving is more important than the actual amplitudes of the samples itself. Okay, why the sequence is so important? Let us take the case of, for example, your photograph. If you take, okay, and if you take your photograph and jumble the pixels basically, so all the pixels that are there originally in your photograph are also there now in the jumbled photograph. But if you provide that as some and tell that it is my photograph, nobody actually sees your face there. So what is lost there is the information among the sequence of pixels is lost. So originally there is some information among the sequence of pixels. In the jumbled pixels, the actual pixels are there. If you plot the histogram, both of them will have the same histogram. But unfortunately, both of them, you will not say that both of them are conveying the same information. So that is why sequence information is extremely important when we are processing the signals. Okay. So then why we are interested in extracting this information that is embedded in the sequence of samples? Because typically the signals that we are interested are processing has a system that is on the backside of it that is producing this signal. We may not have access to the system that we are processing, but we will have access to the signal that it is generating. For example, a doctor looks at the ECG signal and then he tries to basically assess about the condition of the heart. He cannot cut open the heart right away. Okay, but what he has access to is, once the system is there, that is heart, it is producing a signal. So he tries to basically analyze this ECG signal to get the information about the underlying heart that is producing it. Same thing is true even in the case of synthetic signals, like let us say the radar signal basically. So we wanted to process the signal that is getting reflected from the aircraft, okay, to process and find out whether there is an aircraft or not, presence of an enemy aircraft or not. If the aircraft is there, what could be the direction of travel, what is the velocity, and what are its coordinates. These are the things that you wanted to find out. You do not have direct access to the enemy's aircraft, but what you have access is a radar signal hitting it and coming back. So we are interested in processing the signals mainly because we wanted to extract the information that is underlying the underlying system is actually embedding into it. Okay, so that is why we process the signals to extract the information about the system. So with this, so that means that when we are processing signals, sequence information is important to us. Okay, that sequence information, it conveys the information about the system that is underlying for the generation of the observed signal. Now, if we come to the neural networks, the first neural network that we see is basically a dense network. Okay, so it is similar to what an electrical engineer will study in EE 101. Okay, first we start with basically electrical networks. When we are teaching, we start with a resistor network. Okay, but then we will say that after no matter how many number of resistors we keep and how big a network we make, okay, with only resistors, we realize that the voltage or current across any branch or across any nodes basically in the network that is full of only resistors will be just a function of the instantaneous input. Okay, it cannot have any memory, such a resistor network. So that is why we say that means that it can process only the current sample. It cannot see the sequence of samples and process it basically. But we are interested in seeing the sequence of samples to process. Okay, for example, let us say that you have to decide whether you have to invest in a particular share or not. Okay, you do not actually invest in the share by just looking at today's price. You will see, okay, what is the last 1 month's how this share is doing. Okay, every day is this one. Is it in a rising trend? If it is in a rising trend, I would like to invest it because I hope that the slope will continue to be positive and I will gain basically. I cannot just see today's price and invest in that. So resistor is like basically invest based on just today's price. The any current or voltage is just a function of instantaneous input. So such a network is not useful for basically analyzing the sequence information, or it will not offer any memory. We say that they are memoryless systems. The equivalent of that in the neural network that I have seen is basically dense networks, basically. Okay, so the output of a dense network, okay, is nothing but a function of a non-linear function of the instantaneous input. It does not see how we arrive at that particular input. Okay, it does not take a sequence of inputs, a sequence of samples and process it. It takes sample by sample and process each sample separately. So just like a resistor network does not have any memory, the dense network also do not have any memory. So in electrical engineering, what I see as resistors, basically a network of resistors, is similar to basically, except for a non-linear counterpart here, it is just a memoryless system with instantaneous output. So immediately we put down that, okay, the dense network, feed-forward dense network is not useful for me to process sequence of samples or equivalently the signals. Okay, then we will start. Okay, with the moment we say that resistors are no more useful, resistor networks, then in the analog electrical engineering, we'll just go towards basically studying the inductors and capacitors. Inductors and capacitors will help me in actually accumulating the memory. So when we are designing the analog filters, we will use the inductors and capacitors, okay, when to design the high pass filters and low pass filters like that. If I come to the digital domain, because discrete domain, okay, the equivalent of the filters can be designed, we call them as basically, we have two different options to design filters in the discrete domain. We move to discrete domain for several reasons, from analog to discrete domain. I am not going to discuss those things, okay. So let us say that in the discrete domain, we will have two options to build the systems. One is a finite impulse response filter, and another is an infinite impulse response filter. Okay, so that means if you are feeling that your system has only finite amount of memory, okay, or if you need only a finite amount of memory, we are good with actually designing the filters using a finite impulse response filter. Okay, so FIR systems basically it takes the input x of n. Okay, it does a what we call a weighted sum of the inputs. The weights are decided by the W of n. Okay, Okay, if the weighted sum goes in a particular way, we call that as a convolution filter, convolution basically. So the FIR filter can be realized using convolution, just like that WN convolved with X of n. But one thing that we have to notice is the WN has only finite number of non-zero samples, remaining all the samples are zeros. So that equivalently basically translates to, we are seeing the signal, we are seeing finite number of samples at any time instant, and we are computing a weighted sum of the finite samples and taking that as the output. So it offers some amount of memory. So the amount of memory is finite. Okay. Now the question is, what is that we can do if I need infinite amount of memory? Okay. So infinite amount of memory, I could realize that by making that k going to infinity. Let us say that the capital K is the order of the filter, finite the impulse response filter. If that k becomes infinity, then I can actually realize it becomes a infinite memory system. But k going to infinity, that means that I have the weights which are, the number of those non-zero weights are infinite. I cannot even represent it on a computer because I don't have infinite memory. I might have terabytes of memory, but that is not infinite still. Okay, so I cannot represent if k going from 0 to infinity goes, basically I cannot represent them on a computer. So we cannot implement a system with infinite memory the way actually I have written here. That is summation over k equal to 0 to infinity. So instead, what we will do is we will play a clever trick in the case of IIR filters by saying that I will go with basically what is called a recurrence relationship. I will say that a simple recurrence relationship, I can write it as, okay, y of n equal to a times y of n minus 1 plus xn. Whatever I have written on the top is basically a generalized version of that. A simple version is yn equal to a times yn minus 1 plus xn. Notice that this yn minus 1 itself, I can write it as a times yn minus 2 plus xn minus 1 plus xn. So this recurrence relationship, in fact, has basically, I will argue that it has infinite memory, because yn minus 1 depends on yn minus 2, yn minus 2 depends on yn minus 3. So this simple recurrence relationship basically actually offers me infinite amount of memory. So I cannot directly implement it as summation over k going to 0 to infinity, but I can actually implement it as a recurrence relationship where the current output is written as a linear combination of previous output plus the current input. Okay, so the current output, actually we are making it dependent on the previous output. Okay, yn depends on yn minus 1, yn minus 1 depends on yn minus 2. Okay, this offers me infinite memory. So this is what, if wherever we need infinite memory, or if we feel that there is a signal that is generated by auto-regressive process with infinite memory, we will try to use basically IIR filters to actually simulate it or to model that. Okay, so these are the two filters that are available to me: finite impulse response filters and infinite impulse response filters. Okay, now when it comes to building the filters, I can choose any of these two types. I can build a filter that is that can be built using a FIR filter or IIR filter. It depends on whether my model suits the process which is generating the underlying signal. The model will be selected according to that. We have three different types of ways of estimating these W's. The crucial question is, who will give me these W's, the filter coefficients, or here in this case equivalently the A case and B case. These are the filter coefficients. How do we estimate these filter coefficients? Of course, there are different methods in classical signal processing. I will call them as basically classical filters are those where we have precisely know the frequency response. Let us say that I wanted to build a speech enhancement system for power against the power line frequency disturbances. What I mean by is, suppose let us say that you are on an online call with somebody and you have connected your laptop to the powers because your battery is draining off. Okay, and you are taking a call on that, then actually the other person may complain that there is some noise. Okay, the moment you switch on the powers, he will start complaining that there is some noise, especially your laptop is of basically a cheaper quality, not a pretty expensive one. So in that case, what happens is there will be the power line disturbance depending on which country you are, either a 50 Hz power line or a 60 Hz distortion, and its corresponding harmonics also will be there in the speech signal. So then he will start complaining, then you have to basically switch off the mains to actually discuss with him. But then if battery power is draining off, you have to be on powers. Then you will try to actually, okay, I will design a filter to remove this power line frequency. Okay, so to design that filter, basically you have to create a filter whose frequency response will have passes all the frequencies except that one frequency, either a 50 Hz or a 60 Hz depending on where you are staying. So to design this filter, actually you may take a IAR filter or a FIR filter to design the filter. Basically you take the filter and put 2 zeros at this particular frequency, so it is easier to design it as using a FIR filter. Okay, so you can do that and then get away. But in this case, we'll just directly go for designing a filter that particularly eliminates a 60 Hz component. That we could do because, okay, we know the frequency response of the distortion precisely. On the other hand, in some cases, you may not know the frequency response precisely. For example, if you are sitting in a room where there is a AC noise or a fan noise is there, then you do not know exactly the frequency response of those things. Okay, so in those cases, basically you will try to go for these optimal filters, but let us say that AC noise is stationary, it is not changing with the time. So then you will try to actually build an optimal filter to remove the AC noise. On the other hand, if you are in a railway station where the background noise is continuously changing with the time, so a stationary filter will not work to remove the ever-changing frequency content of the background. So in those cases, you will go for the adaptive filters. So classical filters we will use when we know the frequency responses precisely. Optimal filters we use when we do not know the frequency response, but we know that it is not changing with time, it is stationary. And then the final one is adaptive filters. We do not know, we have to adapt to the environment, and also it has to change with the time. As the environment changes, our filter coefficients also should change. So these are the three kinds of filters we will study in signal processing. Okay, just to explain the optimal FIR filter, let us say that if you are wanted to retrieve, basically, let us say that we are having a desired signal D of n, which is basically observed in the presence of noise. V of n is the noise. So we don't have direct access to D of n, but we have access to the noisy observation X of n. So the question is, how can I retrieve basically D of n, which is a clean speech signal, from the noisy observation? So X of n is the noisy observed signal. Then I will try to design a filter W of n and to come up with an estimate of the desired signal D hat of n. Then how should I estimate the filter coefficients? I have to optimize these filter coefficients such that the error between the estimated desired signal and actual desired signal, okay, is minimized. So this error is nothing but D of n minus D hat of n. So estimate W of n such that this error is minimized. So that is how we will pose the problem in the optimal filters. Okay. So in order to estimate the W's, we will try to basically use, when we say what are the best coefficients, what are the optimal coefficients. The moment you say optimal in what sense? We have to decide, or we have to basically tell some kind of a criterion. So one of the criterions is basically minimize the squared error, basically. So least squares. So take the error and find out the error, the squared error, okay, expected squared error, and try to basically minimize the error. So D of n minus D hat of n, I have written it as W of n convolved with X of n. It is just basically, this is just a multiplication, Wk into X of n minus k. This is basically convolution of Wn and X of n and whole square. Okay. you can do this. You can take this J of W here. Basically, D is known to us and X is known to us. Okay, and then take the derivative with respect to W and equate it to 0. You will come up with a solution of W. Optimal value of the W is Rx inverse Rxt. Okay, so this is called a basic Wiener filter in the case of signal processing. Okay, so but one question that you will ask is, you are saying that you don't have access to the clean speech signal, but actually you are taking error from the clean speech signal, d of n minus d hat of n. If I have the clean speech signal, why do I do even this optimization? Okay, while writing the criteria, it may look like actually you need access to the d of n, but actually you don't require access to d of n in the solution. Solution actually contains only a statistic. Okay, RXT, the cross correlation between the desired signal and the observed signal. That is all that is there. Okay, that means that observed signal should be correlated with the desired signal. If observed signal is completely independent of the desired signal, then definitely we cannot retrieve the desired signal from there. Okay, so all that we need is some kind of what is the correlation between the desired signal and the observed signal. If that is there, we can actually come up with the filter coefficients, and we use the filter coefficients to come up with the enhanced signal d hat of n. Okay, just before going, I'll just note on the implementation. You can actually implement the Wiener filter as W equal to Rxx inverse Rxt. If I expand that, okay, I can write it as X transpose X whole inverse into X transpose D. Okay, this is very familiar to the machine learning people. They'll say that it is basically pseudo inverse solution to the linear regression problem. Okay, but in this case, X follows a particular structure basically. Okay, so you see that the structure is written here and the D is here, and you can compute all the coefficients that are given to us and compute the W's and use it. Finally, one point that I want to make is that W's are independent of time. W's are not changing with the time. That is the same filter. We are assuming that is going to work now, and the same filter is going to work after 1 hour also. Okay, I am not going to change the filter coefficients with time. So if you estimate it once, you just keep it and just keep running any amount of time. That is the same filter coefficients. Our filter we are assuming that the filter is stationary. The filter coefficients are not changing with time. Okay, I have not mentioned in this derivation, basically our implementation of this, there are several assumptions. We assume that the desired signal and the observed signals are jointly weights and stationary. And while actual implementation, we will also impose ergodicity when we are actually implementing that. So those assumptions are there when we are actually coming up with this solution to the inner filter. Okay. But then we will say that such a filter will not work if I have to enhance a speech signal when I am sitting in a railway station. I am talking on a mobile phone from a railway station. Sometimes there will be train horn could be there, sometimes train approaching, sometimes train leaving, or somebody actually back in the background, some vendors selling something, those voices will be there. So the frequency content of the noise is changing all the time basically. So an optimal filter that is designed is not going to work now as well as after a few seconds basically, because the noise has changed. The same characteristics of the filter are not going to work. In those cases, how to basically handle? In that cases, what we will say is we will go for adaptive filters. What do I mean by adaptive filters? We make this W dependent on N. The filter coefficients are now dependent on the time instant. They are changing with time. Now earlier the filter coefficients are constant throughout the time. Now filter coefficients are changing with the time. And now how to estimate those filter coefficients? Now the filter coefficients themselves are changing with time. There is no point in taking error expectation over the entire time. When the filter coefficients are themselves changing with time, what is the point in taking the criterion over the entire time? Now, to estimate the instantaneous filter coefficients, you basically look for the error around that particular point. So that is why we will take the error, okay, we will weight it with a forgetting factor lambda n minus k. Okay, now if you can see that if lambda is 1, we are employing a weight of 1 throughout, basically till this point n. On the other hand, if lambda is less than 1, okay, we are giving more importance to the points that are very close to the current instant where you are estimating the filter coefficients. Obviously, you have some reason that the recent past is going to influence the current instant rather than what happened 1 hour before. Okay, so you are giving more importance to the recent values. Okay, so using this, basically you can rewrite the filter coefficients. You can take the derivatives with respect to Wn and solve for them again. Okay, you will get a solution which is looking similar to the earlier solution, but now actually the autocorrelation function and the cross correlation functions start depending on time. Earlier, the autocorrelation function and cross correlation functions are independent of time, basically. That is where we invoked the concept of jointly weights and stationarity condition we invoke, and we'll make them independent of n. But now, since we are assuming that the filter coefficients are changing with time, I am also computing time varying statistics. The statistics are not invariant to time. The statistics are changing with time now. So we are computing these coefficients. Okay, and the W lambda will in all these equations, actually I have absorbed the effect of lambda into these equations. Okay, you have to take care of the lambda, the forgetting factor, when you are writing, when you are forming these autocorrelation function and the cross correlation functions. But where do these helpful? These kind of filters are helpful when the conditions are changing with time. Okay, so these are the two kinds of filters that we have: optimal filters and adaptive filters. Okay, now let us come to the, with this background, basically this is the background that I have when I actually started looking at the neural networks. One is I will use FIR filters, that is finite impulse response filters, when I am interested in, when I have some knowledge that I need only finite amount of memory. If I need infinite amount of memory, I will move to IIR filters, where I will use basically the recurrence relationship. Okay, and in both these cases, the filter coefficients can be either stationary or could be changing with time. If the filter coefficients are stationary, I will use optimal filters. If they are basically non-stationary, then I will use the adaptive filters. So these are four categories I have: FIR, IIR, stationary, non-stationary. Okay. Now with these four categories, now let us have a look at the neural network architectures that we have. Obviously, we have in the first slide itself, we have ruled out the dense networks, saying that they are not useful for processing the signals because the current output is just a function of the current input. Now let us have a look at the CNN. In the case of convolutional neural network, what we are doing, we are taking a block of data. We are taking a block of data and we are doing basically the weighted sum of these values, and we are taking the multiplying with a weights and then taking a weighted sum and then for taking a non-linear operation. So this W case will help in taking the weighted sum, and this G is the non-linear operation. So if I remove that G, okay, the non-linear function that is there here, okay, then it is just a FIR filter basically. Okay, that is WK convolved with X of K. The G is basically to do the non-linear operations, because the main limitation of the signal processing filters, they are only, we assume that the filters are linear. Okay, that means that the input and output have linear relationship. In case when there is a non-linear relationship, actually my FIR filters or IIR filters that I traditionally use will fail. So that is where neural networks are coming to help, there to help us. So G is a non-linear function, whether it can be a tan H function or nowadays ReLU is being used more commonly. So G is a ReLU or a tan H or a sigmoid depending on your application. But otherwise, what is sitting inside that non-linear function is basically a FIR filter. Okay, so FIR, the output of the FIR filter passed through a non-linearity is basically a convolutional layer. Non-linear convolution is what is happening there. Okay, so the output of the nonlinear function is a linear weighted sum of the input sequence. Now I am processing the sequences, unlike in the case of dense networks. But one thing that we have to notice is it offers only a limited amount of memory. Okay. However, in the case of FIR filters, for the Wiener filter solution that I have shown, okay, even though I have not discussed, we can prove that that is the optimal solution. There cannot be any other filter that gives a lower error than that. But such kind of guarantees I cannot have in the convolutional neural networks because of the non-linearity that is involved. Okay, and model parameters of W are going to change, are going to be same throughout the time. Okay, when I am using convolution network, whether I am at the beginning of the utterance or at the ending of the utterance, the same W's are going to apply. The W's are not changing with time. Okay, and then another important question is, what should be the length of the K? How much should be the order of the filter? Okay, so that depends on how much memory that you need basically. So typically, if you want larger amounts of memory, it is very difficult to train those filters, because in the case of the linear filters also, the filter coefficients, the solution is Rxx inverse Rxt. This Rxx will be of the order of k cross k. If your filter is of kth order, then Rxx will be of the size basically k cross k. Inverting large matrices is difficult basically. So what we will do is, even if you wanted to train longer filters, the filters of having larger memory, it is very difficult to train higher order filters. So what we will do is, we will try to build multiple lower order filters. Okay, that is what we will do using subband filtering in the conventional signal processing. What we will do is, higher order FIR filters are computationally complex and slower in convergence. So what we will do is, we will divide the signal into M subbands. Okay, let us say that we are processing a signal of, which is having a maximum frequency content of 4 kilohertz. That means that it is sampled at 8 kilohertz basically. So it has frequency content till 4 kilohertz, 0 to 4K. So rather than building the filter which filters all the frequencies together, we will break down into 4 filters basically, 4 regions. 0 to 1K, 1 to 2K, 2 to 3K, and 3 to 4K basically. So we will use band pass filters and break down into different bands. We will design those band pass filters in such a way that when we add them back, we will get back the original signal exactly. Such filters are available basically. Okay, so we can do that. So we can do sub-band filtering, and then each band you process separately. Okay, so do basically use a subband filters. Basically, these are the subband filtering. Once you do the subband filtering, now originally, since I have a maximum frequency of 4 kilohertz, I might have sampled at 8 kilohertz by going by Nyquist theorem. But now after subband filtering, I need not sample each of these subband components at 8 kilohertz, because each of them has a maximum bandwidth of 1 kilohertz. I can sample each of them at 2 kilohertz itself. So what I will do is, after doing subband filtering, I will downsample all of them. I need not actually operate at 8 kilohertz. I can operate at much lower rate. Now you build multiple filters to process each of them parallelly. Now I need not process sequentially, because I have different bands. I can process each one of them parallelly. You process each band separately, and then you upsample the individual bands and then put them together to get back the enhanced signal. So this is what we will call it as subband filtering when we are doing the when we have to build large order filters. Now you just see the convolutional neural networks. In the case of convolutional neural networks, we will use multiple filters. We just do not use a single filter in a layer. Okay, you will just use something like 64 filters or 128 filters of some particular kernel size. Kernel size is like the model order here. Okay, so we will use multiple filters. When we are using multiple filters, each filter will work as a band pass filter. Okay, so once you pass it through multiple filters, then all the filters you need not operate at 8 kilohertz. So that is why you are having the pooling operations or subsampling operations after the convolutional layers. So the subsampling layers or the max pooling layers in the convolutional layers are actually motivated from their signal processing counterparts, which are basically the subband filtering, what we call it. So convolutional neural networks are quite a few routes in the signal processing. If we see the signal processing, the similar thing is happening. Otherwise, if we do not understand this concept in the signal processing, it is very, very difficult to understand why the subband, average pooling or max pooling is there, basically there. Okay, but only thing is here the filters, in the case of convolutional filters, the filters are basically lent adaptively rather than basically deciding it as 0 to 1 kilohertz or 1 to 2 kilohertz. The filters themselves are lent adaptively with the data and then followed by the subsampling layers or max pooling layers or average pooling layers, whatever we call. That is mainly the working because each of them is functioning like a band pass filter. After band pass filtering, I need not operate at the original sampling rate. I can afford to basically reduce the sampling rate and work at lower sampling rates. Okay, that is why subsampling and pooling layers in the CINNs basically motivated by the subband adaptive filtering. Okay, and multiple smaller convolutional filters are used. That is why we use smaller filters. Basically, we don't try to build large filters in the convolutional layers, but we increase the number of filters. So the filters are expected to learn the bandpass versions of the input. Okay, initializing the different bands may improve the performance. That is why here I wanted to quote you the paper on sync nets. Okay, in order to actually specifically guide them towards learning the bandpass filters, we will initialize them with sync pulses because a sync pulse in the time domain actually translates to a rectangular pulse in the frequency domain. That means that we are forcing them to learn the bandpass structure basically. So sync nets were shown to perform slightly better than rather than starting with random weights. Okay, so in certain applications, it may not be true across the applications. Okay, so the outputs of the filters are subsampled and pooled as we have discussed earlier. Okay, so in the signal reconstruction tasks, basically that is why we'll see the encoder and decoder architecture. Encoder actually progressively subsamples the signals and come up with the lower dimensional embeddings, and then decoder uses the transposed convolutions to upsample the network. So that is basically the upsampling operation that we have used in the subsampling filtering in the regular signal processing. Okay, so with all this, basically one thing that we have told is the multiple number of filters are helping in learning multiple filter bands. Okay, if we see the similar thing happens in the transformer networks, we are having multiple heads. Okay, multiple heads helps in learning the characteristics of the signal across the multiple bands. So this you can observe if you are working with the single dimensional signals like speech. That is what we have observed in the speech enhancement when we are working with. Okay, now what I have told is convolutional filters are similar to FIR filters. The filter coefficients are not changing with the time. Okay, and the subsampling layers are max pooling layers that we use. Average pooling or max pooling layers we will use are similar to the subsampling layers we will use in the subband filtering. Okay, and then coming to the transformers, especially with causal masking, basically. So convolutional filters do not offer us time varying filters. What should I do if I need time varying filters? That means that I need to perform a convolution such that Wn of k convolved with x of k. That means the filter coefficients are dependent on the time instant at which you are doing the filtering. So this is what we'll offer if you see the transformer networks. The transformer networks, what we will do is we will take the x, the input, and we will do multiple linear transformations. And the linearly transformed ones, we will compute the attention. Okay, q transpose times k. Okay, if you write the q transpose times k, if I write it here, it is x transpose WQ, WVX. Okay, if these are basically identity matrices, okay, for the sake of argument, this is basically X transpose X. That is what I am doing in the linear filtering actually. So what we are doing here is we are trying to find out how a frame at the ith time instant is related to a frame at the jth time instant. That is what this Aij matrix, the attention matrix, will contain. How two frames that are separated at ith time instant and jth time instant are related. Okay, now okay, that I could do using basically X transpose X, like the way I have done it in the Wiener filters. Why WQ and WX? Notice that these transformers are actually coming from the language domain, text domain. So why we should have, the question that we ask there is, why should the correlation be basically symmetric? Why, if X is related to Y in certain way, why Y should be related to X in the same way? Okay, let us say in the case of text, if you are coming across a word am in a sentence, okay, if you come across the word am in a sentence, with all 100% probability there should be a I in the sentence. Definitely, without I, am will not occur. On the other hand, if I come across I in the sentence, am may occur or may not occur. I could have a sentence as I have or I was or something like that. But if am is occurring, I has to be there. So we will say that the attention that am gets from I should be different from the attention I gets from am. Why should it be symmetric? So to break the symmetry, we will use these two additional linear transformations WQ and WV. There is no reason to use two weights other than providing more parameters for the model to learn. In fact, you can actually design a network by calling it as a separate matrix basically. Okay. We need a matrix where we need some kind of a transformation that breaks the symmetry basically. Okay, so that is what we will do. Other than that, the equations actually flow similar to that. So finally, in the transformer, what we will see is we cannot write this as a simple W convolved with X. You will see that it is Wn convolved with X. Okay, I'm not going through the equations. So this offers you, the transformer offers you still finite amount of memory, but it offers you the time varying coefficients. So it is not surprising that wherever you are having signal with time varying characteristics, if somebody actually codes the transformer is working than a convolutional neural network, it's not very surprising, because it offers you basically the time varying filter coefficients to learn adaptive filter coefficient, this one. So where the time varying noise is there, okay, obviously a adaptive filter should perform better than optimal filter that is actually learned at one particular time instant. So similar way, transformers offers you still an FIR filter, but a time varying FIR filter. Okay. Now both of them are FIR filters, still finite amount of memory only. What if I need basically infinite amount of memory in my applications? So that is where we are having recurrent neural networks, where we have infinite impulse response can be actually represented or implemented as simple recurrence relationship. Okay, you see the recurrence relationship here and look at the equation of the recurrent neural networks. The recurrent neural networks, what are we doing basically? We are taking a weighted sum of the current input and the past hidden state. Hidden state is basically Hn minus 1. So it is like basically yn minus 1 is replaced by Hn minus 1 here. So the current state of the recurrent neural network is written as the linear weighted sum of the past weighted state of the recurrent neural networks plus the current input. Since we are basically making the current state depend on the previous state depends on previous to previous state, so it in theory it can offer basically infinite amount of memory. Let us not go into practice and talk about the gradient vanishing and things like that is not my goal here. I wanted to basically establish that in theory it is similar to the FIR neural network IIR filters that we use in the networks. But here again, the filter coefficients are not changing with time, the W1s and W1s. If you want to change it with time, okay, you have to come up with some kind of a representation where I make this Wxn of x plus Whn of n minus 1. I have to make it dependent on the time instant at which we are working on. So that is where, just like we use three linear transformations, in the case of transformers, we will use the query key and values, basically WQ, WV, WK, and use them to come up with some kind of a time varying filter coefficients. In the case of LSTMs, we use these three gates basically, the input gate, forget gate, and output gate. So these three gates we will use to come up with the time varying filter coefficients. Okay, if you rewrite the equations for the LSTMs, okay, you can see that the Hn finally depends on the weights associated. So Hn minus 1 multiplied by Fn. Basically, this is a time varying coefficient. This is In, the weight. So this is a time varying coefficients. So we will bring in time in varying components into the recurrent neural networks using these three gates into the LSTMs basically. So that is where the LSTMs offer us the time varying IIR filters are equivalent to time varying IIR filter in non-linear domain. Okay. So to summarize, I have these FIR filters, I have IIR filters, I have time varying filters, time invariant filters or stationary filters, I have time varying filters. So if I have to put CNNs, I have to put it as a non-linear counterpart of time invariant FIR filters. Okay, and I have to put transformers as time varying counterpart, time varying FIR counterparts in the non-linear filters. Okay, and this is RNN time invariant filters, and here it comes the LSTMs. Okay, so the feed-forward neural networks are basically memoryless systems. They are okay actually to model the random variables, but signals are actually the outcomes of random processes. So they are not good enough actually to model the random processes. So that is why we discarded them in the first slide itself. Well, so when it comes to the convolutional architectures, they offer us basically the finite memory with fixed weights. That is why they are actually close to optimal FIR filters. On the other hand, the transformer architectures offer us time varying filter coefficient, WNs. They are dependent on WNs. So that is why they offer basically time varying FIR filters or adaptive FIR filters. And recurrent neural networks offer us basically optimal IIR filters is equivalent to the optimal IIR filters in the nonlinear sense. And in the case of LSTMs, basically they offer us time varying IIR filters in the nonlinear sense. So I think I'm close to the time, basically 10 o'clock. I have only 3 minutes. Thank you very much. So if you have any questions, I would be happy to answer. So the take home story is depends on basically which architecture to use depends on how your process is generated or how your data is being generated. Does it have infinite memory or finite memory, or do you have some evidence that it has time varying distortions or time varying parameters involved in its generation? So depending on that, you can take the right choice of the architecture. And if you know the signal processing, it is bit easier actually to see the architectures that are available in the neural networks. They have a close relationship. Okay. As far as I have seen the deep learning architectures, this is all the summary that I could get. I could not get anything more than this. Of course, I am wearing the glasses, I am wearing the colored glasses, and I am seeing the entire world with color. So I am wearing the glasses of signal processing and everything. I am seeing it from the signal processing point of view only. Okay. Thank you very much. Your voice is not clear. It is, I think you are far away from microphone maybe.
So is my voice audible? Sorry, is my voice audible, sir? Is my voice audible, sir?
It is audible, but there are breaks. It is intermittent. Okay, please go ahead.
Okay. Okay, again, thank you, sir, for your speech, and we are very much happy with your talk. And thank you very much for your presence here. Thank you so much.
Okay, thank you very much. Yeah.
Murthy, thank you so much.
Okay, sir. Thank you. Thank you. Yes.
Thank you. Thank you.
So, on behalf of our INCAPS workshop, I feel honored to introduce Professor Vineet N. Balasubramanian. Vineet N. Balasubramanian is an associate professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Hyderabad, and was also the founding head of the Department of Artificial Intelligence at IITH. His research interests include deep learning, machine learning, and computer vision. His research has resulted in 150 peer-reviewed publications at various international venues, including top-tier venues such as ICML, CVPR, NeurIPS, ICCB, KDD, AAAI, and IEEE FAMI with Best Paper Awards at various recent venues such as COTSCOMAT 2022, CVPR 2021, workshop on causality in vision, etc. His PhD dissertation at Arizona State University on the conformal predictions framework was nominated for the outstanding PhD dissertation at the Department of Computer Science. He serves as senior PC or area chair for conferences such as CVPR, ICCB, AAAI, IGCAI, ECCB with recent awards including Outstanding Reviewer at ICLR 2021, CVPR 2019 and ECCB 2020, etc. He is also a recipient of Teaching Excellence Award at IIT Hyderabad in 2017 and 2021. Google Research Scholar Award in 2021, NASCOM AI Game Changer Award in 2022, and Game Explore CSR Award in 2022. He is going to deliver talk on causality in explainable AI. We are truly delighted with your presence, sir. I kindly request you to take over the session. Now the floor is yours. Thank you.
Good morning. Thank you very much for the kind invitation and a very kind introduction. Thank you very much for that. Okay, I hope people online also can hear me. So please feel free to make the session interactive. So I do have an hour, but I like to keep it as informal as possible. So my talk is physical, so probably allow some interaction for those of you who want to stop and ask questions. Feel free to stop and ask questions at any point. Sure. Sure. Thank you. Okay. So the title of this talk is Causality in Explainable AI, Motivation and Methods. And perhaps the premise for this talk is this growing need for explainability in artificial intelligence. I think everybody's been talking about it from various scenarios. And if you actually look back at where machine learning has been successful over the last decade, I think all of us see machine learning being used everywhere. You're probably using it right from your morning till you go to bed, be it when you check your emails, the spam filter, or your Facebook recommender posts, or your Amazon recommendations, or it's there everywhere around you from morning till night. But if you sat back and looked at all of these successes, you'll notice one thing that's interesting. All of these successes of machine learning that we see so far are in applications where the outcome is actually not risky. Okay, you get a bad product recommendation on Amazon, you lose 1,000 rupees, you lose 2,000 rupees. It's actually okay. You don't lose a life. You're actually okay to take that risk. Right? Or if you get a bad movie recommendation, you lose 500 rupees, you lose 3 hours, but you don't lose a life or an arm and a leg. Right? Let's take another scenario for the moment. Right? So we also how COVID impacted us over the last 2-3 years. Considering how advanced machine learning has been over the last decade or so, you would probably expect it to be used somewhere, like on a daily basis. But go back and see where all it was used in the last 2-3 years. Where you were diagnosed for COVID using machine learning anywhere. Did any hospital say you cannot come and see a doctor, go to the robot assistant, check a machine learning model, and then come and see a doctor? Nowhere really. Right? Nowhere really. Despite the maturity of machine learning that we talk about. Why? These kinds of applications are risk-sensitive applications, safety-critical applications, which means a bad decision means a life, right? Or if you're talking about, say, earthquake prediction or a cockpit navigation scenario, we're probably talking about losses of multiple lives with one bad decision. So in these kinds of scenarios, it becomes extremely important to have the need of explainability for AI ML models. So to know where or how a model arrived at a particular decision. So many countries in the West have already regulated this as a legal process. You have the European Union's what is called GDPR, or General Data Protection Regulation, which actually mandates that a business using personal data for automated processing must be able to explain how the system makes decisions. Right? So you could look at this and say this is all a first world problem, right? So this is all a Europe's problem, America's problem. America has something called algorithmic probability. In India, we're still struggling for our next meal in many places, right? So why do we worry about this? But there is a context. We live in a very globally connected world. So somebody could be working in an Infosys or a Cognizant or a TCS and developing software for a bank in Germany. Right now, the customer goes to that bank and they get a loan decline through a machine learning algorithm. They now have the right through the European Union GDPR to go back to the bank and say, why did the bank arrive at this decision? And who will the query come back to? The guys like Infosys and TCS who has to answer that query, right? So we live in a very globally connected world. This is not a first world problem, but a problem for all of us at this point in time. Even India has the NITI Aayog has released an entire two-part document called the Responsible AI Strategy, and explainability, transparency, accountability form very, very important component of this entire strategy for NITI Aayog. So NITI Aayog did this sometime during COVID, sometime in 2020. They have an entire two-part document on how to responsibly use and deploy AI in India, and explainability, transparency, accountability form a very, very important component of these strategies. More fundamentally speaking, if you go to Wikipedia, you'll actually see that there's something called right to explanation. So we never thought about this in the context of AI in the past. Right to explanation typically meant from, let's say you got a credit score rating, or you went somewhere and somebody just gave you a doctor just told you some diagnosis. You have the right to ask how they arrived at it, right? So it's a fundamental right that you have to explanation. So far, we never looked at it from an AI point of perspective, but the questions have started now coming because AI is deployed so widely around. It becomes very, very important for all aspects of AI. A lot of the work that has been done in AI and explainability has been the last 6-7 years. In fact, a lot of this development started in 2016 when DARPA, which is the Defense Advanced Research Projects Agency in the US, DARPA is also known for its initial efforts on developing the first internet or the DARPA. So they launched a huge funding initiative on explainable AI in 2015, and that's what really sparked off a lot of people to work on explainability. And in the last 6-7 years, there has been tremendous amount of development in this space. Today we have, there are entire tutorials on this if any of you would like to know more. I'm not going to focus on that today. But today, be it whether from a core machine learning perspective, where you're trying to understand which feature was most responsible for an outcome, or you look at it from a broader AI perspective, a planning perspective, a computer vision perspective, an NLP perspective, a robotics perspective, people who work on explainability in all of these domains at this point. Because in different domains, explainability means different things. So it's fundamentally a very subjective topic. So it means different things, and people have developed different algorithms for different scenarios over the years. If any of you are interested in any specific thing, there's a very nice tutorial series. You just change the year here and you will get different versions of this tutorial. I think the latest one is this one called XAI Tutorial 2021 from GitHub.io, and it has a listing of various methods that could be of interest. There are also online books if you'd like to know more. The big question now is, what do we really mean by explainability? So when we talk about evaluating machine learning algorithms, obviously we measure the performance using something like accuracy or precision or recall or a mean average precision if you're looking at detection or a few changes like this based on what task you're solving. The question then is, what does explainability really mean? Right? So it is the elephant in the room, but it's also the proverbial elephant that's now being touched by five blind people, each of whom thinks it's a different thing. So depending on who is using it, if it's a functional perspective, people view explainability from different perspectives. A business owner may be interested in understanding whether they can trust the decisions of the model. A data scientist could be interested in understanding, is this the best model that they built? Maybe from the explainability, I can backtrack and find out how to improve my model. Maybe one feature was most responsible for an outcome. Maybe I should weight that model, right? Maybe I can change my model to weight that model, right? So I can change my model based on the explainability that I get from the model. Or a simply IT ops kind of a person, they simply want to just debug the model, right? So they just want to understand how to debug the model because there's some issue happening. The model is not functioning as expected. They may want to just debug the model. From a law or audit or regulation perspective, governors, people at the governance level, they want to understand the decisions are fair. It's now, today machine learning is used to distribute waste in the country. Are we distributing it fair? Are the needy people actually getting it? These become important questions to ask. And finally, a customer support person may just want to understand, some customers asking them, how do I answer this customer complaint? So that's all they may be interested in at that point. So different people need explainability for different things. from a functional perspective. So even from a technical perspective, it looks like it depends on who is building the solution. There are different kinds of ways you can approach the problem. Primarily because explainability itself is a subjective topic, right? It's very subjective as to what it really means. So in fact, I think formalizing it more clearly and having theory behind it, I think is still an open problem at this point in time. We still don't know about it. We'll talk about that towards the end. But if one had to look at the different methods that have been developed over the years and see how they can be categorized, on one hand, you could look at what are called post-hoc explainability versus intrinsically interpretable methods, where in one case, you built an AI model, it's already been deployed. Somebody just wants to know how the model arrived at it. So you build a layer or a wrapper around the machine learning model and explain it. This is the most common way because people don't want to disturb what's already deployed, what machine learning models are already being used. Those are post-hoc explainable systems. On the other hand, we want intrinsically interpretable systems where the model is interpretable by design. Example would be a decision tree. Decision tree is interpretable by design because the outcome of a decision tree is a series of imperial rules which you can use to explain how you arrived at that decision. Going back to that customer and bank example, if you use the decision tree for it, you can track the decision tree for that particular customer and say that this customer did not get a loan because their credit score was less than 600, something like that, right? So you can actually give an actual answer for it to use the decision tree. Which of these is better? Clearly intrinsically interpretable. Because if you have two different modules for prediction and explanation, things are going to get very complicated. Because then if something goes wrong, whom do you point a finger to, whom do you sue, becomes a very important problem in those kinds of scenarios. Then you have global versus local explanations, where you get an explanation for a specific data set, or you have an explanation for an entire data set or a subpopulation of your data set. You could have methods that's agnostic to what machine learning model was used, SVMs, neural networks, density trees, whatever it is. You can use the same method on top of it, or you could have model-specific approaches, which is tailored to one particular algorithm. You probably use some math in that algorithm to deliver an explanation. Similarly, you could have feature-level explanations, concept-level explanations. You could have action-level explanations, attributions, causal versus correlation explanations, which we'll focus on for the rest of the talk. Or just whether you're trying to make the model transparent, just understand which weights were triggered if you're talking about a neural network, or you actually want to reason in a human understandable language. Right? So you can explainability can mean different things in these kinds of contexts. Right? So it's really an elephant in the room. We still don't have an answer to this, but the answer may be actually allowing different definitions. So maybe I really believe that if one wants to make machine learning models more interpretable, explainable, you need to look at it more as a software artifact than a machine learning artifact, which means you need to have user requirement specifications and cater to those user requirement specifications when you deploy your model. So the more software engineering paradigm probably comes in there you deploy machine settings. In terms of, so we have been doing a lot of work in this space for the last 4 or 5 years. She's also here. She's been contributing to some of these efforts in our group in the past. So we've been looking at both works from post-hoc explainability and intrinsic explainability. One of our earliest efforts was called GradCam++, which is widely used around the world today. In the post-hoc explainability setting, we've been looking at both non-causal methods as well as causal methods. And in the intrinsic interpretability setting, where you develop models that are interpretable by design, we also have non-causal and causal kinds of approaches, all of which have been published at reasonable venues. But what I'm going to focus on for the rest of the talk today is actually these causal methods, talk about why they are required in explainability, and then go into more details as to what we try to do. So one of our earliest efforts in this space was called GradCam++, which was published in WACO 2018. It's a pixel-level weighting scheme for computing gradients, while we provide saliency maps for understanding how a CNN looked at a particular image. Very simple method, but it's gained a lot of traction. It has been used over the last few years, which is, I think, gratifying as an academic to see something actually being used. It's used for explaining COVID-19 diagnosis, chest X-ray images, finding defective cells in solar arrays, explaining cancer prediction, identification of pathogens in chromograms, so on and so forth. It has over 1,000 citations at this point, and the code gets used practically by all people around the world for computer vision, CNN-based explanations. Okay, so now coming to the focus of the rest of today's talk is about causality in explainable AI. So why do we think about even causality in explainable AI? What does it really mean? And I'll probably talk about a couple of our methods in this direction, which are probably complementary. Okay, fundamentally speaking, it's understood from a statistical perspective that causation and correlation are very different things. Everybody gives a very popular graphic such as this. This is an example. There are many such graphics like this if you search on the web. This is an example of a statistic where you have the months along the x-axis, and the blue curve denotes ice cream sales, which peak in summer, obviously, and also shark attacks, which also peak in summer, because a lot of people go spend time on the ocean side in the summer, if you take a look at countries around the world. So if you now gave this data, let's say both of these were in the same data set, and you gave it to a machine learning model. Now the machine learning model is going to assume that as shark attacks increase, ice cream sales increase. Right? So that's what it's going to assume. Right? So because one of them is an input variable, one of them is an output variable, and it will perfectly work out. Right? Because as this goes up, it will nicely correlate and it will predict increase in shark attacks. Right? But clearly we know that this is of no practical relevance from a semantic perspective. So, but this is how machine learning models learn today. They just pick up correlations that exist between data and realize that, okay, certain variables are going up when the outcome is like this. So whenever this goes up in your test data, that means this is going to be the expected prediction. That's the intuition for doing this. So clearly this kind of a data is going to not really get the semantics what is happening until. Right? So one needs to look for causal relationships between data to be able to explain. So I'll probably give you one more example from an explainability perspective. Right? So let's say you are trying to predict, say, risk of heart attack in patient records in the hospital. So if you just took all patient data and gave it to a machine learning model, you'll realize that for pretty much all patients who had a high risk for a heart attack, their blood pressure may have been high in their patient profile. Now, the model is going to think that whenever a patient's blood pressure is high, the risk of heart attack should be high. The truth is, it's only correlated to that outcome. It's not causal for the outcome. There is something else which is causing an elevation in blood pressure as well as the risk of heart attack. You need to be able to isolate these two, and that's where the role of causality and explainability becomes important. Right? If a doctor just told you that your risk of heart attack is high because your blood pressure is high, I mean, how is it helping me? I need to know what I need to change to bring my blood pressure low, and hence the risk of my heart attack to be low. Right? So how do I find that causal variable is what we're going to talk about over the next few slides. So here is a quick, very one slide primer for understanding causal effect. So this is very popularly known as Simpson's paradox in causal literature. Simpson's paradox states, so let's consider a contemporary example. Let's assume that there are a couple of vaccines for COVID-19, A and B, right? Covaxin, Covishield, whatever you call it. Let's say it's A and B. So you have two treatments, A and B, for COVID-19. And I'm quite sure all of us have probably different vaccines. So let's say that the condition C of a particular person who took the vaccine could be mild or severe, and the outcome could be alive or dead based on whatever happened to that particular person. Let's now say that you collected statistics from a particular geography, and statistics said that people who took vaccine A, the mortality rate was 240 out of 1500, and people who took vaccine B, the mortality rate was 105 out of 550. So vaccine A had lower mortality rate. Right? I mean, if you have this table, the company manufacturing vaccine A would put this on all their advertisements. And what would you think? If I was giving you these two options, which vaccine would you prefer? A, right? Lower mortality. So I should probably go for it. Right? So that's what could be advertised anyway. So that's the mortality I should probably go for. But there is one level of detail that's missing here, which is what called as the confounder. The confounder here could be actual condition of the patient when they were given the vaccine. If you expanded the same statistic and looked into what happened behind the scenes, you will notice that vaccine A was given to a lot of people with mild symptoms, of whom 210 passed away. And vaccine B was given to a lot of patients with severe symptoms. Now, if you look at this, while the total mortality for vaccine B is 19% and 16% for vaccine A, if you look at it condition-wise, you can count the numbers and check whether the numbers. You'll actually see that for mild patients, mortality rate was B was low, For severe patients also, mortality for B was actually low. This is known as the Simpson's paradox. Overall mortality wise, A is low. But if you actually take condition wise, both conditions, the mortality of B was actually low. Now, if this table was given, which vaccine would you pick? B. The answer actually is it still depends. Okay, the answer is it still depends. Right? So it looks B, you can take the same B, but it still depends. What does it depend on? It depends on how the graph or the data was actually generated, which is called as a causal graph of how the data was generated. So it actually depends on the causal graph. If you had a setting where the condition influenced the treatment and the outcome, then you should go for treatment B. I assume that all of you assume that to be the case, and that's why you say treatment B when I showed this table. But if you had another setting where the treatment influenced the condition, if this was the causal graph of how the data is generated, then treatment A may still be okay. So, which means it actually depends on how data is actually generated. The problem is in the real world, we actually don't have access to this causal graph.
Yeah. So when we are comparing, so like this, right? So when we compare, we have to compare apples to apples, right? So the number of samples in the case A and case B are completely different, even though you take the percentages. For example, in the case B, the remaining cases are approximately 950, right? 950 less in B, right?
Yes.
Yeah. For example, that 950 could be disastrous, right? So yeah, I think when we go for this comparison sort of things, I think don't you think that plays an important role, having the equal number of?
Absolutely, but if you see how machine learning is practiced, nobody checks for that. Right? So you just look for overall accuracy based on whatever test data is given to you. Absolutely, you're absolutely right. But in practice, you finally evaluate on whatever data is given to you.
Yeah.
That's what you have to practice. Absolutely right. We ideally should be balanced.
Yeah.
But unfortunately, the practice doesn't reflect the way people do it. But this is known as the Simpson's paradox, right? So it looks like one treatment was actually the preferred treatment if you looked at statistics in a particular way. But if you delve into the details, the other treatment is actually better on both counts, not just one of the counts. It's actually better on both counts. This is this is one of the motivating examples for studying causality in general, understanding the notion of what are called confounder variables, which could be influencing other variables in your data set. So where is causality used in machine learning? By the way, causality is not necessarily a machine learning topic, it's a statistical topic. It's been studied in statistics for decades together, not necessarily from a machine learning perspective. But over the last decade or so, a lot of people have been trying to bring principles of causality into machine learning, primarily so that when you build machine learning models, they can keep these principles of causality in mind to build more robust systems. That's the objective in this particular setting. And one of the foremost proponents of causality in machine learning has been Julia Pearl, who won a Turing Award for his work on causality in 2014, I think. Julia Pearl, by the way, is also the father of Daniel Pearl. You've heard probably as a journalist who went through really part of his experience, so there's also other side to Julia Pearl's story. But Julia Pearl was actually won a Turing Award for his work on causality, and he's been a strong proponent. He's over 84 years old, and he's still very active about proposing the use of causality in machine learning. And he proposed a pretty interesting three-level causal hierarchy of how causality can be absorbed into machine learning. So if you look at where we do machine learning, as supervised learning in general today, we typically compute what's called as the conditional probability. We compute the posterior, which is effectively a conditional probability. That's what we compute, typically P of y given x, which is denoted as association. What is the activity? We are actually seeing a sample and then trying to identify which class it could be. Right? We are actually seeing a sample and then deciding which class it could be. So examples could be, what does a particular symptom tell me about a disease? So if I see a symptom, what is the probability of a particular disease? This is what supervised learning effectively tries to do across different applications. But if you actually see human reasoning, there are different levels to it. Right? The next level is what one could think of as intervention, which is P of y given do of x comma z. Do stands for what is called as intervention, which means you set a particular variable to a specific value and see how the outcome changes. So this could be something like, what if I take aspirin, will my headache be cured? I have not yet taken aspirin. In the earlier case, you already see a symptom and then you see what's going to happen. But in intervention, you are trying to see, okay, if I had this symptom, what could my disease be? Right? That's intervention. Right? So we're intervening, everything else kept the same. If I only intervene on one particular symptom, we want to see what's the probability of a certain outcome. A third level is called counterfactuals, which is P of y, yx, x prime, y prime, which is about the ability to imagine. So you could say, was it the aspirin that stopped my headache? I don't know, right? So I don't know. Or what if I had not been smoking the past 2 years? How would I have been? How would my health have been? Unfortunately, we don't have that option. We cannot live alternate lives at the same time, right? So such things are called counterfactuals. Factuals is what a particular data point is at a point in time. A counterfactual is what if something had been different in the past. So what would it have been? Right? So that's what counterfactuals are. So all of this become very important from a causal literature perspective. Right? Machine standard supervised learning, we only look at display. But as human beings, we are capable of imagining, we are capable of reasoning. Right? So we are actually, not that we are correct all the time, but we are capable of imagining and saying, okay, if I had done this, what would have, maybe I should have done that yesterday, right? I would have benefited today. We are capable of this reasoning. Right? How do you endow machines with this reasoning is perhaps one of the questions that's being asked. So where is it used? It's used in explainability, it's used in counterfactual generation. Can I now take one of your photos and say, how do you look if you had blonde hair? How do you look when you're old? Right? So we all see this on the apps, but they're all examples of counterfactual generation. Disentangled representation learning, causal effect identification, causal discovery, fairness, domain generalization, simple regularization, and transfer learning. It's being used across many different applications over the last few years. Okay, so I have about half an hour. So over the remaining half an hour, I'll probably about 25 minutes and try to give some time for questions. Yes, yes.
So one question is in the generation part. Like for example, most of the generation that you can control from making you over normal correlation based machine learning. And you're talking about counterfactual generation. Sure. So don't you think, because now data is very cheap, right? Associating that is easier because now we don't know what are the counterfactuals. Right? Why do you think we should shift in this direction of counterfactual generation? Like, what are the benefits?
Sure. Yeah. The main difference between simple generation and counterfactual generation, right? You could ask, I have a gang that takes my space and makes me blonde. So how is that different from a counterfactual generation? Counterfactual generation is where you keep in mind the underlying causal model. Right? So because as we talked about, every data has a causal graph. The causal graph could have a conformal level, could have different variables. It's possible that changing one thing should change everything else. Maybe if you make my hair blonde, you also have to make my eyebrows blonde, perhaps. Right? Making only my eyebrows blonde is, you can look at it, making only my hair blonde, you can look at it and say it's correct, it's good, but it may not be true to a causal graph.
But in that sense, like, since we have a lot of data, so these confounder variables will help in creating more and more diverse generations. That will help us in the future, right?
Yes, absolutely.
But with a lot of data also, we can generate diverse samples, right? Because
you can, but how many of them respect counterfactual generation is one way of generating diverse samples. Right? So it is one way of generating. People are using it these days to generate. It is one method of generating diverse samples. This is not different from generating diverse samples. They are not competing. It is one way of generating diverse samples, but the way it is different is it respects the causal model. The other ways of generating may just be arbitrarily changing things. Right? It may not actually reflect how data was generated in the first place. So it may not be then impossible to do something like that. Yeah, artificially it's fine. You can use GANs and make things look pretty and all that. But if you come to realistic applications, so there are, for example, like patient record. I want to visualize how this patient would look if they took this vaccine 1 year down the line. Let's say I want to see. Right? Imagine that would change healthcare. Right? If I knew what this patient would look like if I gave this intervention now, it would change healthcare. If you didn't GAN for that, if you are just simply doing something, right? You see patient looking pretty and you walk off, right? So right? So you need to understand the causal parameters for that patient and accordingly change. That's where counterfactual. So that's why I said a lot of the applications that we see today, which are not risk sensitive, causality is perhaps not that important. So causality becomes very important when it's actually risk sensitive. So, I mean, let's say you're flying an aircraft and you want to find out some issue. There are 1,000 sensors there. How do you find out which of them is resulting in the problem? I mean, I've heard that in an aircraft, typically when you have bad landings or something like that, 75% of the time, they have no clue what caused the problem. Right? They have no clue. They just let it happen until it becomes worse. So now there, it's risk sensitive. Right? So there, causal analysis makes sense. Okay, so for the remaining about 20 minutes or so, I'll try to talk about a couple of R papers in this direction. So some equations at least have to be there, right? So we'll talk about some of our efforts in this direction. So one of the first efforts that I'll talk about is if you already had a trained neural network model, what kind of causal relationships between input and output did that neural network model learn? What kind of causal relationships was that neural network? That may not be the true causal relationships, but what did that neural network learn? I first want to understand. Right? So this work was published, causal attributions in neural networks, was published at ICML 2019. Piyush is one of the authors here. And the complementary perspective to this is if we had access to prior causal relationships, how do we make that into a neural network? Right? So I'm a doctor, right? Somebody came to me and said, give me your data, I'll build a nice machine learning model for you. And as a doctor, I said, I have domain information. Put this also in your model. Currently, we don't know where to do that. Right? All machine learning models are data driven. You give data, you will build based on that. How do you make domain knowledge into it, especially causal domain knowledge? Remember that I'm giving a lot of these examples from healthcare because then you can appreciate the importance for us. Right? So a lot of clinical trials have been conducted over the last few decades. So we know that if you do take a particular drug, this is the expected outcome for a certain kind of patient. That's been studied, it's been archived. How do you ensure that when you build a model like a neural network, that information also continues in the neural network, not purely data based on last 5 years patients or something like that. So how do you do that? There's a second book. This book was published at ICML earlier this year. It's called Causal Relation. Okay, let me start with the first book. This work was joint work with Aditya, Piyush, and Nirvan, published at ICML 2019. To the best of our knowledge, this was the first effort on bringing principles of causality into what is called attribution in neural networks. Attribution simply means, in a broader sense, explainability, how much you attribute the output to any of the inputs. How much each input is attributed towards the output is called attribution. So a lot of people talk synonymously between explanation and attribution. Okay, for a large part, we're talking about which attribute, which feature has the highest attribution towards the outcome. Okay, that's what we want to understand. So to do that, let's first define the notion of what is called the causal effect in general causality literature. When you have, say, binary variables, causal effect is defined as expectation of y, that's your outcome variable. Given that you intervene, remember do means intervention. If you set that variable to a certain particular value, given do x equal to 1 minus expectation over y, given that you intervene and set x equal to 0. Right? So which means I set a variable to 0, I see the outcome. And what is the expectation doing? Marginalizing over all possible other variable values. Okay, and similarly, I set one particular variable to 1 and marginalize over other variable values and see how the output changes. The difference between that is the causal impact of that variable on the outcome. Right? So if I took everything of myself and let's say changed my age a little, let's assume we could do that in a hypothetical world. How much did the risk of, say, a particular disease change? Because then I know how much age is a factor for something like that. Okay, that's what we refer to as causal effect. So similarly, if you have to do it for continuous variables, you define it as expectation of y, do xi equal to alpha. You're setting a particular attribute to a value alpha minus some baseline xi value. When you have binary, it's easy to set as 1 or 0. But when you have a continuous variable, what the baseline could be different. If you're doing the causal effect of blood pressure on this heart attack, we know what baseline blood pressure is, 120 by 80. Maybe you see what is the expected outcome if my blood pressure had been 120 by 80. And now, when my blood pressure is changed to a different value, what's the expected outcome? Then I know the causal effect of blood pressure on my outcome. Okay, that's what we define it to be here. So as I mentioned, attribution is effectively an effect of an input feature on prediction functions output, which is inherently a causal question. You want to know how did a particular feature cause a particular outcome? Okay, that's what we're essentially looking for. But existing attribution methods before our approach were largely gradient based, and our own work on GradCam++ uses the gradients of a model to decide how much a model attributed towards an outcome. Because you can compute, once you train a model, you can compute dou I by dou x. Across the weights, you can compute dou I by dou x, dou xi, and that gradient tells you how much changing a particular input variable affects the output. Gradient is effectively a first principles sensitivity analysis, right? If you change an input variable by a certain amount, how much does the output change? Most explainability methods are actually gradient based, like various kinds of gradients. There are also other family of methods which use surrogate models, where you train your neural network, you get your output, then you use another neural network to explain which feature had which how much attribution. Like you use another neural network, maybe to get something like that. And this, unfortunately, when you use another surrogate network, that is also correlation driven. That's not picking up any causal relationships. Both models become correlation driven. So now, how do you estimate causal attribution from neural networks is what we try to do. So you could view gradient-based methods or perturbation methods as special cases of individual causal effect. Individual causal effect can be defined as you have an input u, you have the expected the outcome y at xi equal to alpha minus y at u. If you set alpha to be ui plus epsilon, if you change ui by a small amount and see how the outcome changes, that's gradient. That's the first principle's definition of gradient. So you could look at gradient-based methods, computing what is called as individual causal effect. But what we are interested in is what is called average causal effect, which is what is typically measured in causality literature. So this is what we want to do for the next few slides. So the first thing is we envision a neural network as what is called a structural causal model. A structural causal model is the actual model that generates your data. Generally, we refer to, if you had this information, you don't need machine learning at all. Right? Because if you typically, a structural causal model typically contains the variables that you have. There is what are known as exogenous or some noise variables. And these functions f that connect each variable to another variable. Remember that if your function between x and y is known, machine learning is not required. Right? All of supervised learning at least is about estimating that function. Right? If you had access to the structural causal model, then machine learning itself is not required. Unfortunately, in the real world application, we don't have access to the structural causal model. But what we're going to do here is envision a trained neural network as a structural causal model. You train the neural network. We are now going to see if you thought of the neural network as a causal model, what is it trying to do? Okay, that's what we want to understand now. So you could now take a standard neural network such as this. Bottom is the input layer, top is the output layer. All these shaded nodes are hidden layers. We want to understand what is the causal effect of an input variable on the output variable. That's what we want to understand, assuming the model is trained. Okay. So because we are not interested in the attribution of a hidden neuron on the output, that's not of interest. We can do it using our framework, but that's not of our core interest. We are more interested in input and output. We can marginalize out all the hidden neurons and write this graph. The hidden neurons exist in practice, but we can abstract out the graph as each of these input neurons connected directly to the output neuron through some functions. Those functions are parameterized by the weights, but it's a function. I can just call it some function. Okay. So this structural causal model now becomes composed of just the first layer and the last layer. L1 is the first layer, Ln is the last layer. F prime are the functions that connect each input to output. F prime are the functions that we want to compute because they are the causal functions, right? We don't have it. We have trained a neural network. We want to understand what kind of causal functions does that neural network run. Okay, that's what we want to understand. Those are F primes. Okay, that's what we want to estimate. So what we do here is we look at this quantity called the average causal effect, which is given as the expectation of y to xi equal to alpha, and is the same expectation for a particular baseline xi value. As I mentioned, this baseline xi value, if for a domain, you knew what the reference value is, you can use that. But in reality, for all variables, you may not have a baseline value. Then what do we do in our work? We simply take the expectation of expectations over all possible xis. So we take that to be the baseline value. That's what it's a very simple hack that we do just to compute that baseline value. Now, the challenge in computing this average causal effect is we have to compute this quantity called the interventional expectation. Why it's called the interventional expectation? It's an expectation given that you intervene and set one variable to a certain value. How is that computed? The way that's computed is like something like this. It has to be integrated over all possible y's the probability of y given that you intervene and set xi equal to alpha. That's
Just one slide back. That's one. So that's not the average value for all possible values of xi. So is it not the average value?
because you have two notation. Because two notation is you are intervening and setting a value.
Here we're talking about the baseline.
Even this is based on the intervention.
Yeah, that is
Which means it may not be in the data set at all. This data point may not even be in the data set. You are just taking.
No. The baseline, how it is calculated is basically the average of expectations for all given possibilities of the xi, right? You are taking, right?
Correct. Yes.
Right? Will that be a good start?
That's a valid question. That's a valid question. We don't have a better option for a general idea. I mean, that's why I said if you knew it from domain knowledge, you should use that value.
Yeah.
But if you didn't have the domain knowledge, you have nothing better to do.
Yeah.
This is the only option we have. So if you knew it from domain knowledge, you can put it in. But if you didn't have the domain knowledge, the only option is take this quantity, average over all xi values and choose that as the baseline. Unfortunately, there's nothing better we can do. If you have domain knowledge, you can change. Definitely change. But that's definitely a valid question. So we're going to compute this intervention expectation. Okay, so I won't bore you with too much math. I'll keep it slightly at a high level. So what we do is we remember we want to compute these causal functions f prime. Okay, those are the causal functions we want to compute. What we do is now we take a Taylor series expansion of L1 is the input layer, Fy prime is the causal function that we want to estimate. We are now going to take a Taylor series expansion of that around mu, where mu is actually the interventional mean for each of the input variables. Right? It's the interventional mean for each of these input variables j, and you took the vector of all those interventional means. And you're now going to compute the Taylor series expansion around it. So you have a first order term, you have a second order term for your Taylor series. That's the approximation that we're going to stay with. Now, if you marginalize this over all input neurons, so you now have an expectation, you're now computing the expectation of this quantity, given that you intervene and set xi to be alpha. Now, the first term will remain the same. There is no, because it's a mean, you don't have to touch it. Okay. The second term, the expectation, the interventional mean of this L1 will become mu. So mu minus mu will get cancelled. This first one will get cancelled, and you will be left only with the third term where you take the interventional expectation term. Okay, that's what you end up getting in this particular context. Now, I'm just rewriting the same thing here on this particular slide. Now, what we do in our work is to assume that input dimensions are causally independent. This is an assumption that's okay to make because in a neural network, there is no connection between input neurons. Each input neurons are independent. Keep in mind that we are computing the causal effect of the neural network, not the original data. Right? We are only computing the causal effect in the neural network. In the neural network, the input neurons are independent, causally independent. So this assumption is the assumption that we make, which means that the intervening input neuron will actually be separated from other input neurons. So if this happens, what will now happen is P of xj, given that you intervene and set xi equal to alpha, will be P of xj, because they are anyway independent, they are deseparable. Right? And which means what you can do now is all the interventional means and covariances of the non-intervened neurons will become the same as the observational means and covariances because of this independence. How does that help us? Which means, remember that once I'm given the data, I can pre-compute all the observational means and covariances and store it with it. I don't even need to build a machine learning model. It's just statistics after all. Right? I can pre-compute it with people. And now what I'm trying to say is that may be enough, not exactly enough, that may be an important part of what I need to compute here, right? Where I can get it directly from statistics rather than have to do something more complicated. So, and to compute the second quantity, this baseline here, we use something called causal regressors, where we obtain this interventional expectation for a few xi values, and for the remaining xi values, we simply use the regressor to predict the value. We found that to be a reasonable approximation. Okay. At the end of the day, when you implement it, you have to approximate it, right? So you cannot directly compute this in practice. So we use some kind of regressors here to be able to approximate the baseline expectation. One last thing of this is that if you notice the Taylor series expansion that we actually have a second order derivative, which is the Hessian here. Remember, f prime is actually the causal functions connecting input to output, right? So that is going to be a Hessian here. And Hessian of a neural network is notoriously difficult to compute. So what we do here is simply use some simple linear algebra tricks to instead of actually computing this Hessian, we show that it's enough to compute the product of a Hessian and one of the vectors of this covariance matrix. So this is a common trick people use. It's called Hessian-free approaches to computing this. So instead of computing the Hessian, you realize that what you need in this term is only to compute the Hessian vector product. So you compute that directly using 3 forward passes of a neural network. We show that you can actually compute that using 3 forward passes of a neural network. And using that, we're now able to compute the causal effect of an input on the output. Okay, so I'll keep it at a high level now. I know that I cannot cover every detail in this talk. If you're interested, happy to talk offline. But that's the overall approach. And we also show that we can also do something similar for recurrent neural networks, which is actually harder, right? Because you have a time series component. Obviously, the computation becomes costlier for recurrent neural networks, but we actually show that you can also do this for recurrent neural networks. What is interesting with recurrent neural networks is you can say which variable at which time step was causal for a certain outcome. Right? A certain variable could have been causal in the first time step, but not causal later. But something else could have been causal at an earlier time step and not in the later time response. So you can do that using this kind of approach. Sure.
You can't assume the input neurons to be integrated in this.
Yeah. So in this particular case, we actually assume. So it depends on RNN has different topologies, right? So you can have an output directly in the last layer. It depends on which topology you're using. If so, this becomes the new SCM for RNNs, where you see that the output of the previous layer has a connection back to the input of the next layer. Yeah, you have the input of the next layer. So which is the way it comes. So this is slightly changed based on which topology or variant of RNN you actually use. Okay, in the interest of time, I'll very quickly try to breeze through the results. So one of our first results is on the IRIS dataset, where we actually show that the causal effect values that we get on the IRIS dataset matches if you independently build a decision tree learns something like this, that if petal width is less than 0.29, it says it is class IRIS heterozygote. If it is greater than 0.29, and if it is less than 0.69, it's IRIS versicolor, IRIS virginica. And even the causal effects actually match similar kind of value independently. It's not just to validate how well we get such as result. We also show a result on some synthetic settings, and also interestingly, we show it on a data set from an aircraft setting, which is a publicly available NASA data set that has information on bad landings and good landings on aircrafts, where we actually look at predicting a bad landing or a good landing, build an RNN for it, and then try to use our approach in estimating causal effects. And we see that when you have a bad landing, our method actually has a high causal effect for certain parameters in certain time steps. Red denotes a high causal effect. X-axis denotes the time steps, and Y-axis denotes the different feature attributes that you have, different feature dimensions. And for a normal landing, the causal effect is fairly distributed across different times. It doesn't have full impact. While existing methods that don't use causality end up giving the same attribution to the same variables pretty much in both these cases. It's not useful at all. Right? So that's what we show in this particular work. We also show that this kind of a method satisfies certain axioms that you have with attributions and so on. And the work is publicly available on archive and on PFC's GitHub again. A very quick 5-minute brief of the other work that we did recently is what is called causal regularization in domain priors, where if you have causal knowledge, see, so far we only talked about you already trained a neural network, you wanted to find out what causal effects it has. It's good, but limiting in its own way, because the neural network should ideally respect the causal knowledge that's available in the world. Right? So how do you do that is what this particular work talks about. This is joint work with Gautam, Srinivas, and Amit, collaborator from Microsoft Research. So what we try to do in this work is that, first of all, understand that in the real world, we have what are called causal domain priors. For example, it may be known that a student's test score on admission into a college program increases their possibility of getting into a college program. It's a monotonic relationship. As your GMA score increases or SAT score increases or GMAT score increases, you know that the probability of getting into a college directly goes up. You know it has to be monotonic. It cannot be other way. Similarly, increasing the number of employees on a factory's productivity is likely to always increase. maybe it will saturate after a point in time, but it's likely to be monotonic. We know this from common knowledge. Similarly, you could have fairness constraints to say that skin color should not be used probably in a criminal justice kind of a setting. It should not be used, which means you know that the causal effect for skin color should be zero. You should not get any causal effect for that. Right? You know these kind of things. Similarly, you could have U-shaped curves, J-shaped curves. All of them are already known in, say, drug literature or medicine literature to say that a certain particular drug, it'll have an increasing effect until a certain point and then start having a bad effect after a certain point. Right? So these are well known. Now, how do you factor these into causal effects of neural networks is what this work is particularly about. So what we try to say is that if you had some causal domain priors that have certain shapes, how do you ensure that the way we captured causal attribution in our previous work, that causal attribution was actually true to the original causal domain prior? That's what we try to understand in this particular work. We call this credo or causal regularization with domain priors. I'll very quickly breeze through it. To be able to do this, you need to understand the different kinds of causal effects that are available in practice. There's something called direct and indirect effect. A causal variable can be directly responsible for an outcome, or a causal variable could, some other factor could increase my BP, which could therefore increase my heart rate. That could be an indirect effect also, right? Both are possible. Even within that, there is something called total causal effect, controlled direct effect, natural direct effect, so on and so forth. I'm not getting into these details at this point in time. But what we show in our work is that you can regularize for three kinds of causal effect neural network models: controlled direct effect, natural direct effect, and total causal effect using our kind of an approach. I won't go into the definitions of theorems, but what I'll only talk about is one simple thing, which is an algorithm here. While all of this can seem fancy when we talk about controlled direct effect, natural direct effect, all of that so far, what we end up showing in our work is that the derivative of the controlled direct effect effectively becomes the gradient of the neural network itself. That's what we end up showing using these. Which means what we can end up doing is that while we train a neural network model, in addition to whatever loss you're using, by ERM, we mean whatever loss you're anyway using, mean square error, cross entropy, whatever you loss. In addition to that, you add one term in your loss, which tries to ensure that the gradient of your neural network, which is this grad f here, this M is a mask to decide which attribute should this apply on. Because you may not have the prior for all variables. You may only have a prior for one of the variables in your system. This mask tells you which variables your gradient should be applied on. And you try to match that to the gradient of your domain prior. You match the gradient of your neural network to the Jacobian of your neural network to the gradient of the domain prior, and simply add this to your loss, the gradient of the neural network. We show that this is good enough. This is sufficient. We actually prove that this is sufficient to maintain certain kinds of causal effects in the neural network. It is in the original domain prior. Okay, that's how this is implemented. The implementation is fairly simple for this particular work. And using that, let me just show you one of these examples. Compass is a data set that's used for what is called recidivism. It's used as a criminal justice data set in the US, very popularly studied in fairness literature in the US, where we actually show that if you use only ERM, right? ERM is a standard learning procedure, whatever loss you end up using. If you ideally want to ensure that this accuracy on recidivism should not depend on the race. It's generally understood today that, especially in the US, there have been studies that if somebody is African American, the risk of them being a criminal automatically goes up in small race, right? So, which is unfair to a lot of people that come from that race and color. Right? So, you want to not have that kind of bias in your models. So, you ideally want to ensure that even if you intervene on the African American trait, the recidivism output should not change. That's what you're looking for, right? So ERM basically changes. You see that it actually starts going up. The recidivism goes up as the African American attribute is changed. While what you really want is this flat line, the red line here, and the blue line is using our method, and we show that we go closer to the flat line using flat line approach. Right? We show that not only on this kind of a flat line, we can do this with whatever you want. If you want a monotonic line, if you want a J-shaped line, and any of those lines, by using our method, the causal effect at the end of training matches the causal prior that's actually given by the prior. That's what we end up showing. We show it in different kinds of settings, and our work is again available on archive if you'd like to take a look. Just to conclude in a couple of minutes, just to summarize the other things that we have done in this space. So I'm going to mainly focus on the causal things that we have done recently. So this is the work that I talked about, which is causal attributions in neural networks, which was published in ICML of 2019. And more recently, we talked about causal, this should have been ICML 2022. So causal regularizers is ICML 2022. Apart from that, we've also been looking at can we develop, I mean, unfortunately, data sets for learning causality are very few today. I mean, you need to be able to study them effectively and understand and validate them. We have been looking at developing data sets for causal representation learning. How do you mitigate bias to causal perspectives? I just gave you an example of how bias in the models. You can only reduce bias if you analyze it from a causal perspective. Right? Otherwise, it's always going to take these correlations that could make a model biased on certain attributes. We've also been looking at how do you learn representations that are causally disentangled. Going back to this question of counterfactual generation, you can only generate true to the causal model if the latent variables that you learn are truly disentangled from a causal perspective. Right? They're only changing something will result in a causally corresponding causal work. Right? So that's what we talk about here. More generally, beyond causal literature, we've also been looking at how do you generate what are known as canonical saliency layouts for face models, submodel ensembles of attribution methods. More recently, we've been looking at how do you develop intrinsically interpretable models in neural networks. Right? So where the explanation is baked as part of the prediction itself, it's not something that you have to do as a post-hoc analysis. One specific work I just mentioned is in this year's CPR, we had a work where we try to say if a model, a deep learning model, predicted a particular image as a cat, can you, if somebody asks, why did you call it a cat? If somebody asks me, I will say it has whiskers, it has 4 legs, it has a tail, it has a furry coat, so on and so forth. How do I bake these concepts into the model itself so that the model can automatically say it's a cat because it has these concepts? How do you do that? Is something that we also looked at, which we're also looking to extend in our future work. I think I'll probably stop here with just a summary of some extensions in future directions. One of the extensions in our work, which we've actually recently, just yesterday, submitted to a different venue, is what happens to causal attributions when inputs may not be causally independent. Right? I mentioned that a neural network assumes these inputs to be causally independent. What if it's not independent? What kind of causal effect can you estimate? Is something that we also extended our work to. And in general, one of the fundamental issues when you bring principles of causality in machine learning is they are very, very compute intensive. Because any of these, to compute the causal effect of one variable on the outcome, you have to marginalize over all values of the other variables. That's straight away a compute intensive effort. So how do you do that using various kinds of factors? These are not unknown to us, using things like KD trees and high dimensional compute hacks. How do you actually make these things more feasible is something that we've been looking at. But more generally speaking, from a community perspective, learning disentangled generative processor mechanisms is very, very important. Generally learning, I mean, this is something that's picking up in the world. A lot of people are talking about it. Is how do you do deep learning more fundamentally from a causal perspective? Like when you learn representations, they should inherently represent causal relationships between input and output rather than rely on correlations. How do you do that fundamentally is still an open problem. How do you do disentanglement and counterfactual generation when there are confounders? This is a little tricky to do. It's not very straightforward to do. How, when you have confounding variables which you may not see, then how do you learn disentanglement models and counterfactual generation models becomes important. Also, how do you align causal and compositional representation learning, so on and so forth, could be very interesting directions for as well. More fundamentally speaking, I think the entire notion of formalizing explainability, coming up with learning theory frameworks for explainability, I think is still very, very open. I mean, if I had to just stop with one thought, I just say this, that the entire learning theory literature of machine learning, especially in supervised learning, is premised on starting with the first sentence that says, consider a tuple x1, y1 to yn, x1, y, x and y, right? Which effectively talks about input and output, and all your learning theories are premised on that assumption. But when we ask for an explanation, a third quantity comes into the picture, which is a y hat. We still have an input, we still have an output. But now we are actually asking the model to give a third quantity, which is a y hat. But all our theoretical frameworks are not premised on this. They're premised on only two things, input and output. So how do you come up with learning theory frameworks where explanations are also accounted for? Because they're asking for that in the model. We also have to ensure that foundationally we also develop models that address these issues. I think are interesting forward problems. I think I'll stop here with yeah, acknowledgement to all the students and our collaborators and of course the sponsors for this work.
Again, we thank you for everything. Comparative certificates. Gratitude to you.
Thank you so much.
So I request participants to take your to access the refreshments with the back door. You can access this textbook. Refreshments are arranged. You can just come back again. So I want you people to settle down fast. A warm greetings to everyone. I feel honored to introduce Professor Saket Nath, sir. So J. Saket Nath is currently working as an associate professor in the Department of Computer Science and Engineering at IIT Hyderabad. Prior to that, he served as faculty at IIT Bombay for 7 years. He is interested in machine learning with a focus on kernel-based methods. He received his master's and PhD degrees from IISc Bangalore and bachelor's from IIT Madras. He is going to deliver his talk on controversy versus time meets Mercer. Thank you, sir. Thank you, sir.
Thanks, Anna. Thanks to the organizers for inviting me here. So today I'm going to talk about two different metrics that measure distances between probability distributions. The first one goes by the name Cantor-Lorentz process time. And the second one are based on so-called Mercer kernels. So though both of these measure distances between distributions, they have very different properties, okay, complementary many times. And so what we will see is, so towards the end of the second part of the talk, we'll see our attempt, which is a joint work with Piyushi and Pratik, to bridge the gap between these two different metrics. So let me start by introducing the first family of metrics, which are popularly known as process time metrics. So as I was saying, see so what these metrics do is they given two distributions, they tell you how different they are. They in fact measure some kind of a valid distance between them. Okay. So here's an illustration. So suppose you have a source distribution. So here is a discrete distribution where actually got in the mass function. So these masses are currently abnormalized. So at y1 there is 1.5 mass, y2 5 units mass, so on and so forth. So the total mass is I think 9.5. So the normalization constant is 9.5. So that is one distribution. Suppose you have another distribution. This is just for illustration. So another distribution, x1 some value, x2 some value, and so on. Okay. So what do these metrics do? Given two distributions that give you a number which might how different they are, how far they are. Okay. Now the way Cantor-Lorentz process time metrics do it, compute this distance, is actually by solving a very intuitive problem, which is called as the optimal transfer problem. So let me explain that problem. So here you have the same situation, the same distribution source target. But let me give you a interpretation to these distributions. Suppose these y1 to y4 represent locations of 4 mines, okay? Mines with ore and metal ore. And then suppose these x1 to x6 represent locations of refineries which process these ores. Okay. So now, 1.5 at y1 basically means there is 1.5 units of ore present in the mine located at y1. Similarly, a 1 here at x2 basically means at the refinery x2 you can process 1 unit of ore. That is the maximum capacity. Okay. Okay. Now, so there are various, so the ore is inside the mine. You have to somehow transport it to the refineries to get it processed. Okay. So one obvious question is what is the plan for this transportation? Right. So whether you will transport 1.5
units to this entirely, or transfer 1 unit to this, half to this, or in some other way, right? Finally, so once you do this plan and transport, no mine should be left empty, left with an ore, and no refinery should go empty, right? And that is possible in this case because the amount of ore available in mines is 9.5, which is same as the capacity of the processing total capacity, right? Which is also 9.5. So this is called the transportation problem. One way of imagining how the solution to these problems will be by looking at so-called joint distributions. Okay, so suppose phi is a joint distribution whose marginal is source and target. What it actually means is, it basically means the following, whatever we have been saying here now, it will give me a valid transport plan. Here is how. Suppose I find that, so what is the joint distribution? If I add all of these numbers, it should add to the total quantity. So that's the idea. Right? So suppose I take the joint distribution pi with 2 units and 3 units at these coordinates, and give the interpretation that, so suppose I interpret that from y2, the mine at y2, I take 2 units of ore. First of all, I can do that because there are 5 units, only 2 units I'm taking, and then I'm transferring to the facility at x1, right? And that's also possible because the maximum capacity of the facility is 2, right? You understand? So similarly, but once I transfer these 2 units to this, I will be left with 3 more units. Perhaps I can send those 3 more units to this location, and that's a valid assignment. That's a valid transportation plan. Okay? So like this, so I gave you just one example of a plan, which is same as a joint distribution, right? But there are multiple such plans possible, right? How many such plans are possible? As many as the number of joint distributions pi, whose marginals, that means if we marginalize over x separately and y separately, there should be s and d. And such number of joints is uncountable. So how many plans are there? Now, obviously, when I'm actually transporting, I want to do it minimum cost, right? I want to do it efficiently. So suppose you are given some kind of cost of transferring a unit ore from a particular mine to a particular site, right? So these are locations, right? So I can actually calculate distance, roadway distance, or petrol cost, or whatever, right? So suppose I'm given these costs, okay, at each pair, x and y. Now I can define a score for each plan, right? What is the score? It is simply sum of, if this is 2 units transferred, 2 into the cost of transferring from this to this, right? So every pi value at a grid point multiplied by the cost value at the corresponding grid point, and just sum it over. Then you get the entire total cost, which in terms of the joint distribution is nothing but the expected cost. So for every transport plan, I now have a way of scoring it, how good it is, which is nothing but the expected cost. Of course, because in this example, because these 2 distributions are discrete, the integral, the expected cost will simply be the sum of these cost and pi values at each of these grid points. Okay. So, which is the plan that I should select? The optimal plan is the one which minimizes this expected. The problem of optimal transport is exactly problem of optimal transport. So you need to, so what is given in an optimal transport problem? We are given 2 distributions, source and target. We are given a cost between the support points of these distributions, and then which are like these x and y points. Right? Then you are asked what is the optimal solution to this problem, which is same as the optimal transport plan. Okay.
So now in the previous example, I gave a illustration with discrete distribution. The same can be replicated with continuous or one discrete, one continuous, all kinds of. Now it's a mathematical problem. So this is a purely optimization problem, right? Okay. Now, now, now it is easy to see intuitively that suppose these two distributions are very different. Right? Suppose these points are actually, so the points here are nearby to the points here, and the points here are nearby to the points here, and so on and so forth. Okay? So these are locations of the mines, right? These are locations of refineries. Let's assume that these axes are such that I placed them in some kind of an order. Okay? So actually a point here, a location here is similar to a location here. Say. Okay? Now in such a case, if I take a distribution which is very different from this, what will happen? What will happen to this value of the optimal transport cost? So for example, suppose I have the same distribution here, the blue distribution here and here also. What is the optimal cost? What can I do? I can actually transfer points one to one, right? I take this point, I will this point, this point, this point, this point, this point, and I'll get a cost what? 0. Because I have the mine there, I have the location there, I'm just transporting the cost is 0 for us, right? And you can't beat it, correct? So if you have distributions exactly the same, the value of the optimal cost will be exactly 0. Provided, of course, that this cost actually measures some kinds of distance between points. What will happen if the distributions are very far off? Cost will be more. Right? So it looks like intuitively, if you look at the value of the optimal transport cost, it will actually give you a notion of distance between distributions, right? It looks like, but the answer is yes, mathematically you can show this. And that's what is the Wasserstein. So the optimal value of this problem is actually a metric between S and D. It gives you a valid distance in the sense that it will satisfy all the properties like non-negativity, triangle inequality, all these will be satisfied by W. Of course, the requirement, the key requirement is that you should supply a valid notion of cost, which is the distance between the points. So distance between the locations, and now you get a way of measuring distances between distributions of these points. Right? So you give me a notion of distance between objects. I'll give you a new notion of distance between distributions over the objects. Right? Now that is interesting because in many cases, you might want, we will see examples, you might want cases where the way we measure distances between distributions is actually respects the inherent geometry. So we will see examples. But perhaps we should keep this in. So though it looks like a requirement, it is actually a boon. Right? So okay. So in fact, people generalize this and call it P Wasserstein matrix. So you take any distance and raise it to the power of P, say distance square, and take an under root. Then also it's a matrix, but it's a different matrix. So you guys should understand that if I give a different P and different cost, I'll get a different matrix. If I keep C and P same, I can measure distance between all possible distributions. If I change my notion of ground metric, I'll get another way of measuring distances between distributions. If I change P, I'll get another way. So it's basically a family of metrics we are talking about. So any questions till this point? Yeah, applications we just.
So this would make sense.
So
Transforming a distributed
Okay.
We will have a dual solution analysis. Yeah. Okay.
Information is.
Oh, okay. Okay. So I should stand somewhere or? No, so I should stand at a place.
Just giving the information.
Yeah. So,
Is it a minimization or set of measures? Is it a minimization or measures?
set of measures, okay, that is the joint measures. Yeah, so you can show, so convex circular flow, yes, you can show that this is a convex circular flow. In fact, you can show that this fellow to the power of t, that is also convex. That's convex function. In fact, if t is 1, it's a linear program. 1 to infinity. So coming back to your question, maximum. So I'm just thinking if it has a trivial solution.
This is something saying easiest way to open on this question process.
Mhm.
Will there be merit of talking about the hardest way of
Hardest way. No, that's a very nice question. I've never thought about it. But it doesn't look like there will be a trivial solution. So suppose you take the case where there are exactly same. Then the most difficult way. No, but there are marginal constraints. We should not exceed the marginal constraint. Suppose we have a symmetric distribution, both are same. Maybe I'll point, point on one end to the exactly opposite end. Maybe that will be the solution. But that's not right. But that's not a trivial solution. It's not trivial in any way. So I think, yeah, the problem. I think so. But I have to think about it. So any other questions? Okay, so coming to applications, coming to applications, the probability distributions are inevitable in machine learning. You find them everywhere. So you will see a lot of applications where these things are useful. The most popular ones are from the category of generative modeling. All of you would have heard about GANs, Wasserstein GANs. In this context, these metrics are became very popular. So what essentially you would want to do in generative modeling is you would be given some training set and let S denote the distribution underlying the training set. And let t theta be the likelihood distribution you are modeling. You are trying to model. You would ideally want to get a distribution which is as close as possible to that in the training set, so that you can start generating new samples from the which look like what are given in the training set. Correct? So this is the goal in generative modeling. Suppose theta is your parameter, you would like to find that theta with which the model's likelihood is very close. So how do you say very close? Maybe minimize distance. And one way of minimizing distance is P versus P. Right? So suppose you do this, so you get a lot of papers, and the list is not even close to exhaustive. There are maybe hundreds of papers written around this idea, and some of these themselves have thousands of citations. The first one I think has 8,000 citations. So it's a very popular idea. Right. And Wasserstein metrics have seen a lot of success in such models. Okay. Next application is suppose you have a case where you have two models which you have trained or learned somehow. Suppose one model is at time t is equal to 0, another model is for time t is equal to 1. You have only collected data for t is equal to 0, t is equal to 1. But now suddenly you want a prediction, a predictive model at t is equal to 0.5. How would you do it? So one way of doing is, assume, suppose these two are actually probabilistic models. You can try to compute some kind of an average model. So if it is like t is equal to 5, 0.5 will compute a midway average. If you want it equal to 0.4, we will compute a 1/4 average, so on and so forth. So these problems are called as so-called Barry center problems or average. No, the problem of finding the average, so on and so forth. So look at this problem. So if these mu's were points on the Euclidean space, and lambdas are all say lambda is 1/2 say, then you are basically trying to say minimize, get me a point which is close, whose sum of distance, sum of square distance is minimum between two given points, and that point would be the mean, right? Good point. Now, if instead of you point on Euclidean space, suppose we have distribution, that is say the blue distribution and the red distribution, that is say mu1, mu2. You would perhaps solve the same problem, but instead of using Euclidean distance, you might use the p-Wasserstein distance square. That's what you do. Suppose you do this, you will actually get the green color, which indeed looks like an interpolation, right? So note that the right. So basically, its mean is somewhere in between, variance is also somewhere in between. So it looks like an average. So in fact, if you change the distance function in the Wasserstein method, you will get different interpolations. Right. Then that's what makes the metric very interesting. And somebody actually put this to use. Right. So here is a problem where you are given two objects in 3D, this object and this object. Right? You want to come up with an interpolated object. So these problems, are very difficult to solve. But suppose you imagine this to be a distribution of points in 3D. Right? So this is another distribution of points in 3D. Right? You would like to interpolate such that the inherent geometry of 3D points is respected, right? Right? So suppose you take Euclidean distance as the distance, then you'll actually get this interpolation. This looks very good. Right? These such figures are very interesting. Okay? So yeah.
Really is to come up with the distribution
Which is like in between. So if you take the distance between the green fellow, that is the unknown, that is the mu, and the red fellow, that is the first term, and plus the distance between the green fellow and blue fellow, that is the second term square. You are asking which curve basically minimizes this square of distance, sum of side. Yeah, so here lambda was half. So I want a midway. If you want a 1/4, 3/4, you can put lambda as 1/4, 3/4.
lambda.
No, we want it to be dependent, right? Or
Lambda. So lambda, if you really lambda, if you thinking different.
that's what. So if you put lambda as for the blue fellow 1/4, red fellow 3/4, what will happen? This green will be very closer to the red fellow than the green fellow, than the blue fellow. So you can actually create a continuum of interpolations between the blue and the red. Okay? By varying lambdas. Yeah.
Is it possible to estimate lambda as optimum lambda?
No, see, lambda is, see, I want to, see, somebody you didn't, so perhaps I'll repeat the application. Suppose blue is a model which you have collected data as t is equal to 0. And red is that t is equal to 1. Now you tell me that which other t you want to interpolate. 0.1, 0.5, where 0.7. So 0.7 say, I'll give it lambda as 0.7, 0.3. Right? So lambda is no. So any other?
Another 20. No problem, don't worry. Next session is Murthy garu, Shastri garu. So, yeah, just no problem.
No, it is stop. Okay, so you wanted more on the basics, right? So I'll go slow on the basics then. Okay, so now the next family is a totally different kind of matrix than the ones we saw earlier. Okay, and the way you compute so previously how did we compute the distance? We actually solve another problem, some optimal transfer problem, and then you actually get the distance. Right? So these notions of distance are completely different. So-called kernel, Mercer kernel based distances. They are popularly known as MMD distances or MMD metrics. MMD stands for maximum mean discrepancy. So if I write MMD in title, nobody will know, but Mercer, if I wrote correct, people will know. So I wrote Mercer in the title. So these work in the following way. So they first embed these distributions in a Euclidean kind of space. So for example, suppose this P and Q are discrete distributions, then they can be characterized by their mass function, right? So you can think about a vectorial representation for mass function, right? Where each entry represents the mass at each value the discrete variable takes. So it is easy to imagine how discrete random variables can be embedded in a Euclidean space. But it is not trivial to imagine how densities would be embedded. Okay, and then how computations would be performed efficiently. So there is some clever way of doing this. There's some clever way of embedding these distributions using a so-called kernel-based Euclidean factor space. Okay? So that's what I'm calling as RKHS here. So the blue fellow is represented as a point in the space, and the red fellow is represented as point. Right? So like this, every distribution is different. How do you represent? There is some mathematics behind it. Let's not worry about that. Okay. Now, then this distance between the MMT distance between these two distributions is simply defined as the natural distance in the space. This is a Euclidean space, there I can compute distances. Okay. So basically you embed, there you compute distances. So that's how these things work. Now, so one thing to be noted is the geometry of this space depends on so-called what is the Mercer kernel involved. Now, how is it dependent? Let's not worry too much about it. But this is what essentially these methods do. And in fact, they can be computed efficiently in terms of the kernel. Now, whatever that means, if some of you know kernels, this expression would be fine. Otherwise, also no problem. So basically, you are embedding and then computing distance. Okay. Now, so the key aspect in which MMD metrics are very good is the following. Now, in machine learning, never you are given distributions, you are only given samples from the distribution. Right? So it doesn't matter how good your distance function is if your estimates for the distance are very bad, very poor. Right? See, I don't know the distributions, but I have to measure distance between the distribution. What do? I'll finally approximate it as distance between the sample distributions. Sample-based distributions. Now, if this estimate is bad, right, then however good your distance function is, it's not going to work well. Right? So, okay, in case of MMD, so what do? So again, you have these estimates from the sample, you embed them to compute the distance between the embeddings of the samples. But actual truth is distance between these two fat points. What can you compute? You can compute the distance between these small points, right? Now the question is, how fast does the distance between these two points converge to the distance between these two points, right? If that convergence rate is decent enough, then you can employ metrics. If it is not, then you can't employ this metrics. Now I did not tell you what is the rate for when we come to that, but for MMDs, it is very, very attractive. You can show that it is order 1 by root m, where m is the number of samples. So, and in particular, it is completely independent of dimension. That means it does not matter where you are, which is the space x. It could be a million dimensional space. So it's a density in million dimensions you are estimating. Still fine. I mean, you are not estimating this density, you are actually estimating these distances. The distances go at a very fast rate, independent of how large is your space. Now that should be very interesting because if some of you know, estimating densities in high dimension is known to be a very challenging problem. So if you say it is infinite dimensionality, and somebody should, if you are knowing it for the first time, should be very excited. So accordingly, MMD has seen success in machine learning applications. Of course, you can use MMD in the similar applications as I have told earlier, like in generative modeling. But because of their ability to estimate distances very efficiently, they have seen more success in statistical hypothesis testing. For example, you take a similar problem like gas. Instead of asking the question generate samples, suppose I ask you this question, I have these real samples, I have these fake samples actually simulated. Now tell me, are these closed by distributions or not? Right? So if you are, so that's called two sample test. Okay. So if your metric says that a fake samples are close to real samples, then perhaps your metric is not so good. Okay. But if your metric actually says that these are fake, these are the distributions are not same, then your metric is good. Right? So like that, people have evaluated metrics and found that MMT distributions are very good in terms of identifying such that actually they are different. So real versus fake they can identify very, very well. So as of today's state of the art, methods for two-sample tests are based on MMT distance. So similarly, you can design independence tests, statistical independence tests, so on and so forth. Of course, you can use it as a loss function. But what we have seen, so this is an introduction to both these families. So as we have, so both of these metrics are popular in machine learning as I told you. You can use them in various applications. But what we have seen is for few kind of applications, few metrics are used popular. For the other kind of applications, the others are popular. So obviously, one question to be asked is why is it so? For example, there are less papers we find in generative models using MMT rather than using Wasserstein. Why is it so? So here is one way of understanding it. So this was in this paper. So this is an empirical comparison. Suppose you look at the objective function in generative models. Okay, objective function as a function of the parameter. When using MMD as the loss function, MMD as the function as the distance versus Wasserstein as distance. So something like this is what you will see. And the point to be noted is, so here in this figure, so there is a global minima here, there is a global minima here, but you are having two local minima. Whereas if you look at Wasserstein as a distance, there are no local minima. So this is just an illustration that this is what might be happening. This is not true. So maybe the optimization problem is easier to solve somehow when you use Wasserstein than the MMD. By the way, there is no convexity involved here. Both of these are non-convex, so it's not a. Next, yeah. So what about? So that's the reason why perhaps MMDs are less popular. But what about the other problem? So can I do this, interpolation of objects like we do in Wasserstein? And the answer is no. So initially you would expect that MMDs also would do well in such a problem, because even in an MD, the kernel is there, which actually depends on besides the geometry of your embedding. So perhaps if you change your kernel, geometry becomes good. So perhaps is your hope. Yeah.
Problems MMD is done well.
So these are the problems. Statistical process solved. So these also there are applications, but less powerful. And the reason is parameters. And in such applications, you can't employ MMD because what you can show is if you solve the same problem using MMD as the distance, you will actually get the red curve. And red curve is nothing but the simple average of these density functions. You have this blue density function, orange you simply take a average. Right? You will get actually this red curve. Right? And even if you change the geometry of the embedding space, change the kernel, it will be the same. So essentially, it is blind to the geometry on the data points. Whereas Wasserstein is very vigilant, it uses the metric on the data point. So geometry used by Wasserstein is supposed to be better. So MMD would obviously fail if you do such tape interpolation. Okay, so let me summarize the points. Yeah.
One question. As this Pakistan difference can handle covariance.
What can be used for handling covariance? Both. So it's just a distance, right? You use this distance and distance. So it depends on how you are handling covariance. It is more important than. See, as I told you, the last function has a trade-off. So last function may be good if because it inherently captures the geometry, or it is because of the estimation that it is good. We don't know, right? So currently, if I remember, covariance shift. So both kinds of loss functions are possible, and there is some success with both methods. And which one is data we have? So there actually, so see, the problem is these are not direct evaluations of the metric, right? So there's some downstream, somewhere the application function is covariance shift. And there somewhere one place you use distance distribution, right? So whether something is working because of that or some other thing is not very clear. So currently I would say we can use both. Okay. So let me summarize the findings. So the MFT, so if you look at geometry, it looks like Wasserstein is more interesting because first of all the interpolates you get, that's what I'm writing as notices here, are interesting. Whereas in case of MMD it is a very trivial interpolation, right? It's a simple average of the densities. Similarly, the MMD's geometry is actually Euclidean. So because essentially you go to embed in a Euclidean space, the geometry will remain Euclidean in some sense. So whereas Wasserstein distances, especially for p greater than 1, they need not be Euclidean. In fact, Wasserstein distance, p Wasserstein distance need not even be a convex function. So whereas Wasserstein's to power of p. So for example, 2 Wasserstein square, that will be a convex function, but 2 Wasserstein need not. Next in generative modeling, it looks like Wasserstein. Both are applicable. So in terms of geometry, MMD, so whenever you have a problem involving geometry, interpolation, perhaps avoid MMD. That is the summary from the first bullet. In generative modeling, yeah, so both have their advantages and disadvantages. One is better in estimation, the other is better in the geometry, whatever is there in the problem. But so the success currently more methods use Wasserstein. So it's basically you can use both and perhaps try. The possible explanation is that optimization is easier.
So maybe if you have better optimization techniques, these also start working well. We don't know. So currently there is only one point where assistant is hands-on, right? So this is +1, say this is say 0, 0 points. But there is one point for MMD also. Okay. So the estimation, as I said, is 1 by root x, which is independent of gender. Whereas what you can show for Vas's time is the same rate of convergence. So if you take m samples again, it is 1 by m to the power of 1 by d, where d is the dimensionality of the data. So imagine you are in very high dimensions, this 1 by d will be almost 0. That means your error is not decreasing at all. So you're not converging at all. Okay. So what did I do? So in this talk, I presented two different families of metrics. One based on the so-called optimal transport problem. The other based on so-called kernel-based density. Both seem to have their own trade-offs. And the interesting point is they seem to have complementary properties, right? Where here something is good, here it is not good, something is good, it's not good, right? So they seem to have complementary properties. So what so what we have done in our work is to try to somehow mix these two metrics so that we get both best of both the worlds. And what we have shown in our papers, so I'll just quickly. So that is very, so I don't have time to show it.
It's conceptual idea.
So we use the concept of regularization. That's what we used, but that's not the only way. So I'll just. No, what is it? Yeah. So what we have tried to do is somehow combine these two and come up with a solution where both the advantages are preserved. That is possible through the concept of regularization. That's what we tried to show in a. If you are interested, please. I was trying to show you the references. So our Neurons 20 work and our submission, INCAPS submission. So these are the references which have all the details of how you can perhaps get both the best of both the worlds. Okay, so I'll stop here.
Any questions?
The regularization, actually we have an improved version of assistant language, which is assistant gradient parameter.
So that is the way of solving the optimal transport problem. Okay. So regularization has been, as you are saying, regularization has been well studied in optimization architecture, but not MD based regularization. And what we show is actually that is very useful in terms of improving the sample complexity from 1 by m to the power of 1 by t to 1 by root m.
One or two questions.
That is perhaps possible through so-called MMD regularization, which seemingly nobody has tried. Yeah. Yes. It depends on kernel. It depends on kernel. You take few kernels like also in kernel presented. But if
చాలా
you
మంది
take
వర్క్ చేస్తారు ఈ టాపిక్ పైన చాలా మంది వర్క్ చేస్తారు
See, actually, so that's why we expect that MMD is also respect the geometry because they are
let them take some questions
but the answer is final answer is no because the equivalent is always there. That is very surprising. Why? Okay. Yeah. Yeah. So if you want to put it on manifold, the computations are on manifold. So our computations are all on computers. These are kernel based. That is the advantage. And then again, estimation, everything will depend on the geometry of the manifold. I don't know if there is some interest in understanding for the, clear that. Is that the usual advantages of yeah.
ఏంది ఒక 20 దాంట్లో 20 టాపిక్
So, see, if you do it properly, so I don't have time to show details of that. But if you look at we show how to actually combine them that preserves convexity, that preserves electricity, and gives you sample.
వాళ్ళిద్దరు మెడికల్ డొమైన్ లో ఈ రెండు దివ్య
We are really delighted with your presence, sir. And we were very happy that we have got the complete basic knowledge of what is the metric level basic details we have got through. And most of us have a chance of going through the papers which were being published in the same areas. Like it's an inspiring talk for us, but so that we can just proceed with our works. Thank you so much. And I request Lingareddy sir to give a token of gratitude.
So anyway, the slides are available offline also.
Yeah.
If any questions, you can contact them, right?
Lights.
So good afternoon, everyone. It's my privilege to address Professor Subramanya Sastry Challa. CS Sastry received the PhD degree in Applied Mathematics from IIT Kanpur. He worked at the University of British Columbia as a postdoc fellow and at IIIT Jabalpur as an assistant professor. He is currently with the IIT Hyderabad. His research interests include sparsity-driven methods and their applications. He is going to deliver his talk on sparsity-driven learning with respect to theory and its applications. I welcome you, sir, for your talk and thank you. Thank you.
So, good afternoon, everybody. Firstly, I will address the arguments of this event. Okay. So, I'm going to talk about sparsity-driven learning and sensing. Of course, there is a small change in the title of the presentation. The title is sparsity-driven learning and sensing behavior applications. So, this is the organization of my presentation. There are in fact 3 parts. In the very first part, I talk about 2 basic things, starting with an application.
Then in the second part, I talked about sparsely driven learning. So there the focus is going to be more on learning. Okay. I pick up some of the applications, especially to image processing, and to show you actually how the sparsely driven methods can be applied to rearrange our objective, especially classification, towards classification. In the third part, I'm going to talk about sparsely driven sensing. So there the objective is basically more about sensing. Right? So can we cut down on the data to be used so that actually with reduced data we can realize our objective. So that is going to be the third part of my presentation. Okay. So there are of course two subparts in the first part of my presentation. So to begin with, I start with one application, motivating application. Let us take a look at why actually we need to study the so-called sparsely driven. What is the motivation? Of course, there are many examples, but I pick one application that arises in medical domain. So we all know CT scanning is one. Am I able to properly? Is everything fine?
No, here it is okay. But on this thing.
Okay. So we know CT is actually one popular imaging modality. MRI is another popular imaging modality. Of course, they are using for tomography, especially the data collection carries a lot of importance. Because X-rays are patient is given X-ray dosage, some samples are collected, machine actually CT scanner collects some samples. Based on that, the image is reconstructed. Since the X-rays are harmful to human bodies, so we have to cut down on the dosage to be given to the patient. So in CT dosage reduction carries a lot of importance. Whereas in magnetic resonance imaging, image is very safe scanning modality. What matters a lot is the scanning time. We all take about 40 minutes, right? What is really important is to cut off the time, scanning time. Because during the scanning process, there could be movement, patient will move like this. As a result, there will be error in the measurement. Any error that is present in the measurement can possibly have its bearing on the reconstruction quality. Okay, so for these reasons, so in CT especially, as I told you, versus reduction carries not value. Whereas generally scanning time carries reduction in scanning time carries value. So let us actually try to understand how actually we realize the objective. I'm going to concentrate a bit more on tomography. They actually try to do a bit of modeling and tell you basically how the dosage actually can be reduced. Just some mathematical ideas. So this is where you see that the sparsely based areas actually come down rescue in a very big way. Right? So in CT, what happens? You see the cross section. Okay. You see the cross section. Patient is given dosage. These are all X-rays. This is for one view. This is for another view. Once actually the ray actually passes through the patient, it loses some energy. The CT scanner actually measures the energy loss for several X-rays. So based on the energy losses, actually what one tries to do, one tries to basically reconstruct the other CT. Okay. Typically, CT scanner collects only energy losses for several X-rays. Okay. Let's actually try to understand the discretization. How? Imagine this is the cross section. When I say cross section, I mean just imagine the plane hitting the head like this. What you get is 2D cross section. So this is actually the 2D cross section that is taken here. Imagine the grid that is basically covering this 2D cross section. Now this is the image for us. Okay, so these are all the pixel values, x1, x2, so on, xn square. I am considering the grid of sin by. Okay, so there are basically m square number of pixels. Right? I just considered for the sake of explanation, I considered one X-ray. So we know basically initial energy of the ray. So once the ray comes out of the cross section, it loses energy. So we essentially the machine measures the energy loss. We know both. So energy loss is basically measured with this scanner. This is done for several X-rays. Okay. Now if you put it in mathematical setup, so what happens here? This is the energy loss for a particular ray. Right? So this energy loss is really because when the ray actually passes to the cross section, this fellow actually absorbs some energy, this absorbs some energy, this pixel absorbs some energy. So the total energy absorption, the total energy that is absorbed with the pixels for all in the path of the ray is going to be, yeah. So this is the energy loss here. This is the energy absorbed by the pixel, first pixel that falls in the path of the light. So if you put it in matrix setup, basically end up getting like this. So I consider basically M base, M number of X's. I did not say anything about which race I consider. Right? Suppose we consider that we take actually only M number of races. Okay. Now we have basically these are energy masses. So this is the matrix containing only zeros and ones, and this is basically the vector corresponding to the underlying image. Okay, now see it in matrix setup. So this is something like my input image. Okay. Now suppose, so what is this M here? M is basically M square. Okay. M square is basically the number of pixels within the image. So we know basically suppose we want to reconstruct the minimum size. Say suppose the image is say 1 megapixel image. Then what happens here? This M is 6. Right? This is 10 to the power of 6 here. So the column size of the matrix is 10 to the power 6. So mathematically we know basically in algebra we see that when M is equal to M, the matrix is nice enough, we can have solution. Right? We can apply some method and we will get the solution. Then under ideal conditions, what will be the size of the matrix here? 10 to the power of 6 by 10 to the power of 6. So practically it is very, very difficult to solve. Right? So we have to have an efficient way of reconstructing the underlying image. But I told you at the beginning that we need to cut down the process to get into the patient. Which means I cannot basically have the row side of the matrix to be same as the column size. Right? Because row side is basically about something referring to number of X-rays, number of samples, collection samples. So I want actually practically I want actually the row size to be as small as possible. Right? But anyway, I cannot do anything about the column size because that is something tied to the size of the image. Right? So column size automatically gets fixed here. But the row size actually can be controlled. So what is the way out? So what is the way out here? So that we can have a very small magnifier, which refers to number of X-ray projections. So this is where this sparsity based ideas come into picture. See here, look at the underlying CT image here. As an example, I consider standard quantum image. If you take the gradient of the image, then what happens here? So most of the pixels actually take 0 value. Right? So most of the pixels get 0 value here. If you see this here, only about in the original image, about 42% of the pixels are non-zero. Whereas in the gradient level, about 12% of the pixels are non-zero. Which means there is something happening naturally in the underlying image. The question is, can we exploit? So can we exploit the natural property that is present in the image so that we can have control over the dosage of the matrix, which is actually something tied to the dosage to be given to the patient. Right? So this is actually one motivating example. Like this, actually one can see several examples. So naturally here, if you look at this matrix equation, y equal to ax, x is basically having some property. That property is in the form of sparsity. Sparsity in the sense that many zeros are automatically between 0. So this is where the catch is. So we can exploit this property and basically reduce the size of the matrix. This is what the number of projections. So the number of projections can be controlled drastically. At the same time, we can have the reconstruction of faithful quality. Okay. So this is where the ideas in the field of computer science come to the. Let's try to understand it in mathematical terms. So suppose I have a matrix equation. So we have seen that the application, naturally the problem of dosage reduction leads to an under-renewal system, where the matrix is really fat and short, in the sense that the row size is very small compared to column size. So I have the matrix equation. Immediately, suppose I have noise. This is the noise factor. This is the under-renewal system here. The noise eventually satisfies this property, boundedness property. So we know from simple linear algebra, we know that when we have a matrix equation, especially under-renewal system, it has infinitely many solutions in general. So when there are infinitely many solutions, we can impose the criterion of our choice, right? Say for example, let's see the criterion. Okay, with respect to this criterion, of course, this is nice. Nice in the sense that this criterion is convex function. Okay, then we can have basically a nice solution, unique solution. So this is the criterion, and with respect to this criterion, basically we can have any solution of the matrix equation. As an example, I consider one criterion here. Suppose this criterion, one criterion could be the smallest distance criterion. So among all solutions of the matrix equation, you pick the one that lies closest to the origin. This can be one criterion. So minimum distance criteria. So this will lead to basically what is called the solution. A simple verification. This is the convex function. Of course, the constraint is a convex function here. So this will give us this as a solution. With respect to this criteria, this is going to be the solution. Okay, but see, I consider the star example. So in the star example, suppose matrix A is side T by 100. Okay, I consider a vector of side 100 here, 7 non-zero entries. You see the product of vector. So when I basically solve this optimization problem, with respect to this criterion, if I solve this optimization problem, I end up getting this as a solution. See something global close to this one, right? My target solution is this. Okay, but I consider, when I consider this as my criterion, I get this as my solution. The second one as a solution. This is not good enough. See, look at the CT image, something is naturally happening. So if I consider the standard two-norm criterion here, obviously I won't get the target image. Right? There are infinite solutions. Okay, with respect to that, second two-norm criterion, with respect to this particular criterion, I get this as a solution. Right? But this is actually not a target solution. So we need to basically change the criteria. We need to have some other criterion that in such a way that we get the solution, the desired solution. Okay, that desired the criterion is going to be something called zero norm. So this zero norm is the count per number of non-zero counts in the vector. So let's say the vector you basically count of this is non-zero, this is zero, this is zero. Let's take count per number of non-zero counts, right? So with respect to this criterion, I can expect to get a solution. Right? Fine. So guided by substitution, we pose this substitution law. It's not easy to solve this. Mainly because this is not a fractional problem. So when the size of the matrix becomes big, it obviously actually shoots up very quickly. So in more technical terms, this is very hard. Cannot be solved so easily. And the problem cannot be solved so easily. You actually repose it. Okay. So the reposed version of this problem is something like this is the convex relaxation of this problem. Right? So in place of this, now I can solve this problem. So this is where several mathematical questions arise. What is the guarantee that these two actually result in the same solution? It's obvious question. Right? It can give different altogether different solution. Right? So there are certain technical conditions to be satisfied by the matrix A. And size of the matrix is sparsity of this vector, which means number of non-zero components. Under those conditions, these two actually result in the same solution. Yeah, just one fine. Consider that our matrix is very nice. It is so nice that these two actually result in the same solution. So, what is the way to solve this problem? Simple, this can be recast as a linear programming problem, so I can basically solve this. There are other ways of solving this problem. See, broadly, there are two ways of solving this problem. In the first category, basically we see KD method. Like for example, orthogonal matching percentage one formula. Very formula. So there is another class of methods which are convex in nature. So for example, prediction of convexity is one method. Basis percentage is one method. So using convexity basic techniques, basically one can solve this optimization problem. Okay. This is actually one emerging direction within the field of compression sensing. This is adaptive compression sensing. Like for example, take a medical domain. The medical domain where the patient undergoes this test repeatedly. Take for example, CT scan. Okay. So after undergoing this test, okay, suppose the patient knows that there is some problem in the image. When he basically undergoes this test second time, the information that is deduced from the previous scan can be incorporated. So as a result, basically one can reduce the dosage part. Okay, this is basically adaptive compression sensing. Towards end of my presentation, I come to this. So this is adaptive compression sensing, where we have some information about the signal that is to be recovered. We have some appearing information. So that appearing information can be incorporated into the reconstruction process. As a result, you can have basically what an algorithm, simplified algorithm, or the algorithm that requires basically reduce solutions. So the problem is actually posed like this. So mostly the prior information is in the form of a support. Like for example, consider the case where the patient undergoes test. Okay, tumor is there in some patient, which means what in the image basically I know this location. I know the basically the pixels where the abnormality is present. So that basically accounts for this test. That accounts for this part this TDM. Okay. So this T can be incorporated into the problem. One can basically pose this weighted optimization problem. When you solve this problem, you can see that the target property will automatically be presented in the reconstructed image. Not reconstructed signal. This is all about basics of message sensing. So we posed zero minimization problem. We started with underdetermined system. We considered zero term minimization. Then we considered the reposed version of that, which is in the form of one-arm minimization. So when we solve that, basically you get this vector which contains very few non-zero terms. Which is the basic story about message sensing. Now let us take a look at sparse tree discovery. So there are basically some machine learning application where one can incorporate or one can make use of sparsity and analysis. This is what is called dictionary language. This dictionary language. See, imagine you have a database of images. Okay. With or without label information. You want to basically group them in such a way that in each group we have the images having certain properties. Okay. So this classification problem can be basically addressed through dictionary. What is typically done here? We have a bunch of vectors here. Right? Nothing is known to me. Underlying sensing matrix here. So the underlying sensing matrix can be built here. So how that is done here? This matrix is built in such a way that this theta I is sparse vector for each area. Okay, this is something actually coming from the database, something given to me. So for each area, this matrix can be built in such a way that theta is a sparse vector. So this matrix can be built using this optimization problem. So what is done here? You basically append the source. Sorry, I written P here and I have written A here. What should we have done? This is B. So this matrix is built in such a way that for each area, theta is sparse enough. Okay. So optimization problem, one can implement both this optimization problem. We solve this basically on the critical matrix side. So a way of finding solving this problem is what is called KSVD, case integral conversion, which is the generalization of tables algorithm. You see, this algorithm could take K equal to what is it? Okay. So in the KSVD, what is done essentially? So this matrix capital Y is the matrix 1, where the columns are given by these vectors. These columns are the columns in capital Y are given by these vectors. So some rearrangement is done here. So this step actually can be solved by using similar conversion. For this reason, this method is called KSV. So what is done? You consider this as a matrix here. You take basically first order approximation here. So basically you obtain this vector, this column of the matrix. Do this repeatedly. Then finally actually get this matrix. Okay. So let me take a look at application that is in the form of content-based retrieval. And then you suppose you have a database consisting of large number of images. Okay. So some of the members have one particular property, other members have another property. So for this purpose, the grouping is one application. The second application is the content-based retrieval. You have search images. Right? Suppose search image is given to you, you basically look for similar images in the database. This can be addressed with sparsity setting. Let us see actually how that is done. So we know CPR, there are annotation-based methods, there are actually region-based methods, there are statistical methods actually that use ideas from statistics. There are transformation, there are methods that make use of transformation to like wavelengths. But here actually we show that the dictionary-based methods actually have promising application. So what is done here? We consider the objective of having the retrieval where the retrieval is invariant with respect to transformation, certain transformation. Like for example, there are two images in the database, where one is the related copy of the other. Right? So you can in fact have invariant, rotation invariant retrieval. Not only that, you can have scale invariant retrieval here. So the idea here is we actually connect to the Radon transform domain. So in the Radon transform domain, here suppose you have two images where the rotation angle difference is say on theta. So in the Radon transform domain here, that actually the theta actually shows up like this. Suppose you see the rotation difference between the two images. Okay, in the Radon transform, one can in fact show that this will automatically happen. So r theta is equal to r theta plus theta tilde here. Theta tilde is something that is giving you, see here. These two are actually exactly same image here. The only difference is because of rotation, right? So that rotation can be estimated here. So in the radar transform domain, actually this property naturally exists. So run this actually one can estimate the rotation angle here. The rotation angle can be estimated in this simple formula. You see here, the peak is occurring here, the peak is occurring here. The difference between these two actual peaks accounts for the rotation. That is present between the rotation difference that is actually present in the second degree. Okay, so the rotation can be estimated. So once you basically estimate the rotation, you can basically undo the rotation. You can undo the rotation, thereby you can have the features that are invariant with respect to rotation. While for scaling invariance, what one can show is that this property holds. This mx is something standing for the maximum value in the radar domain. This tx is basically what the support. Radius of the support in the radar transform domain. You basically obtain this ratio. If for a given image you obtain this ratio, suppose you have two images where one is scaled with the other image. If you obtain this ratio, they are exactly same. Which means what? This is of course the vector here. Now this vector, if you look at these two images, these two vectors are exactly same. But look at the underlying vectors. The underlying vectors are x bar and dx. The difference between them is scale. Okay, so there is a scale difference between those two images. But the moment you generate these two vectors, automatically the scale invariance takes place. So you estimate the angle, you undo the rotation, you obtain this ratio corresponding to all images, then naturally the scale invariance follows. So once you do this step, then what would happen? You receive the query, receive the vector corresponding to the query image here. Now, for the given database members, what you do? You obtain these ratios. So you obtain these ratios, automatically rotation and scale invariance take place. Both take place now. You solve this optimization problem. When you solve this, automatically you get dictionaries. You build dictionaries here, you get automatically this clusters. So once you have the clusters, given this achievement, you search for the relevance in the clusters. So that way actually you can iterate the images having similar properties. Okay. So the idea here is that. So behind this optimization problem, whole idea goes like you start with the vectors. You have the database here. You just do some binary cluster. You have a binary cluster. Now for each cluster, you build the dictionary. So after building dictionaries now, you take each and every database member and look for its sparse representation in all these dictionaries. So whichever the dictionary gives its sparsest representation, say for example, for a given vector xj, the first dictionary gives its sparsest representation. Then now actually you put this in the first cluster. So this is basically I update my clusters. After updating the cluster, what I do now? I update my dictionaries. After updating dictionaries, again you basically update your cluster. You just go back and forth between dictionary update step and cluster update step. So finally convergence takes place. As a result, basically finally you have the clusters. So in the clusters, basically you have the members having similar properties. Okay. So once you have clusters, given a set image, you can basically return for please. Sorry, each cluster does it have multiple dictionaries? Yes, no, each cluster has one dictionary. Each is I have many clusters. So I have many dictionaries. So as I told you at the beginning, you have arithmetic rules, C1, C2, CK. Okay. Now for each cluster, you have a dictionary. C1, C2, CK. Now using these dictionaries, you try to have sparse representation of each and every mathematical database. Okay. Now then you apply the clusters. After that, you apply the dictionaries. Okay, you just repeat these two processes. Finally, the stage phase. You end up having basically clusters. Once you have clusters ready,
one question is instead of dictionary learning, have you use EM expectation maximization because the others use the same?
No, see here I am basically sparsely set up here. See, there is some property that is naturally happening in the database metrics. I want to explain that property. For that reason, actually, I am getting dictionaries.
But the parameter of first you're updating the cluster, like the parameters of the clusters, and then you're updating the clusters in the state.
Yes.
Like the same type of expectation maximization can't be used the same methodology because
No, you can use here. See, I told you. See, my interest is what? Take for example, maybe little later on, I will show you the results. You have database consisting of medical images. Okay. So the images that come from one particular department, medical department, have certain properties. Whereas if you look at the images that come from another department, they have another common properties. right? So I basically want to exploit the property. So for one group, there is a property, common property. For another group, there is another common property. For the third group, there is another property. But if I build several dictionaries for all these members, say for example, for the first group, suppose the dictionary is say D1. So this window is able to basically attract, provide sparse representation for the members belonging to that first group. Okay, so that is the intention here. So when you actually solve this optimization problem, so suppose let's say something related to query. This is the sentiment given to me. So database numbers are given to me. If I execute this algorithm, basically I end up having similar looking images. Then we extended this, anyway, see the block diagram of this whole area. We have certain numerical details here. In fact, one can show that this will happen. There is a proof behind all this. Okay, this is execution strategy. We extended this to database. So this is the database consisting of all style images, estimates, like that. So we built actually several dictionaries. So we built several dictionaries. So using dictionaries, given this achievement, see, given this opposition is achievement, these are basically similar to images, primary images. But this is the achievement, these are actually primary images. Okay, this is the performance provided by. So what is happening here? Sparsity is something naturally present. Okay, we actually try to extract it. We try to extract the natural property of the underlying images. Then actually we came out with, of course, there is a learning procedure here. That learning procedure actually gives rise to this argument. Okay. So I talked about the previous application is all about what learning. We have database members. From those database members, we build dictionaries. That is where the learning process takes place. But actually, we use those dictionaries for the classification and then see the database members. Now, this is basically what in the third part, I focus more on sensing part. So look at this. Again, I come to the application in tomography. So we notice in compared back that in tomography, one can have this matrix equation. So one can in fact have this structure. This is something corresponding to one angle. This is corresponding to another angle. This is another corresponding to another angle here. So this way actually you can see the block structure in the matrices. In the matrix also and in the vector. Look at this. So this is for one particular angle here. This is the source here. So the rays are actually passing through the cross section. They lose energy. The energy loss is measured here. So as I told you, objective here in tomography is what? To perform on the dosage. Which means what? I have to basically remove certain rows. Which means I have to remove basically certain projections. X-rays corresponding to certain radiant parameters. Which rays have to be removed? That is obvious. Say for example, suppose I say that out of say 1000 rays, you take only 100. The question that arises is which 100? Right? Within 100, beginning 100, initial 100, or last 100, and what is the distribution? Right? This question naturally arises here. So this is essentially sensing problem. Sensing in the sense that so the all available rays, the theory tells you pick only so and so rays. Pick those rays and use those rays and you can have regular reconstruction. In that sense, actually, this is a sensing problem. So this is another geometry here. What is called triangle geometry? So this is for one angle. This is for another angle here. So typically in folded aperture tomography, so what is done here? You basically block some of the rays. So as I told you, I don't want to use all rays. I want to use only some set of rays, which means I have to block basically some of the rays. So which rays actually have to be blocked here? So one can in fact come up with an algorithm, deterministic algorithm that tells you that you use only so and so rays. Right? You pick those rays corresponding to so and so parameters, then you can have the reconstruction of good quality. So this amounts to basically what? So this is of course the full set of radar measurements here. So this is the diagonal matrix. Consider the diagonal matrix where you have only some of the diagonal entries are equal to 0, some of the diagonal entries are basically 1. Okay. So wherever you have zeros, which means what you are not taking the corresponding rate. So then the question that I see what is the best practice. So the problem of reducing certain X-rays leads to essentially what finding a diagonal matrix Okay, where many diagonal linkers are 0, so the remaining diagonal linkers are 1. Okay, so the question is about finding the cluster diagonal matrix. So this is of course the motivation I stated already. So this leads to what? Now you find this matrix D in such a way that this product essentially has factorized properties. So in the language of compressive sensing, we expect that this matrix to have very small value for coherence. So coherence is something that is related to what you say the better behavior of this matrix. So we want the matrix to be better behaved here. So which means what here we consider the matrix very ideal here. That is very nice in the sense that in a very more technical term, we consider this matrix to be API. So which are actually very ideal behavior. So we find this matrix D in such a way that these two actually remain close by. So these two actually remain close by. These are not correlation problem. So we fix the row side. Okay, out of say 1000 rays, I want to take only 100. So that number 100 is fixed here. This is something different to that. So now this problem actually leads to an optimization problem like this. So this is something matrix A is something actually given by this product. Okay, this is what I'm talking about. So when you solve this optimization problem, obviously what happens? You get the underlying matrix. Okay, so once you know the underlying matrix here, what I do now? Once I know the underlying matrix, here, this once this is known to me. So I know basically the ways that have to be written for vehicle reconstruction. Okay, so this is what here. Mostly in the literature, what people try to do, they pick it randomly. Say you say that okay, out of 1000 rays, you take 100 rays and solve the distribution. So that is basically random way of selecting underlying extremes here. This is the random projection, whereas this is with the dimensional projection. So at this particular subsample rate, we show that we have basically the reconstruction of very good quality compared to the case where the rays were taken with the probability distribution. So this is the deterministic strategy. Deterministic strategy, here again you see that the sparsity framework actually comes to our stage. See, this is rather having sparse structure, right? Many entries are 0 here. Many entries are 0 here. When you pose this optimization problem, what naturally happens here is this vector D is sparse. Right? Be the diagonal matrix, when you vectorize the diagonal matrix, automatically what happens here? Many elements are 0, which means this D is basically sparse. So something is naturally happening here. That property actually has been exploited in order to formulate this optimization problem. When you solve this optimization problem, you get the diagonal matrix D. Very at the diagonal you see many zeros. Okay, so in fact we showed that the complexity associated with this algorithm is proportional to S into M by M by 2. Where M by M is something related to size of the matrix, size of the underlying matrix. Suppose you want to reconstruct an image of size M by M. Okay, so this can actually comes into size of the matrix. This S is actually something related to the number of basically projections. This is related to number of projections here. The best algorithm that is known in the literature possesses this anti complexity. Whereas here we showed that the complexity can be reduced to M5 by 2. That's simply M5 by 2. This is the deterministic strategy. So the message here is that the sparsity framework actually is the sparse structure of the matrix. The diagonal structure of the matrix actually can be explored. That is the message. So here this is the sensing problem. Sensing I don't in the sense that out of 1000 rays I am picking the best 100. Right? So you don't have to acquire all samples. See, what is the meaning of compressive sensing? Earlier people used to collect all possible data. And from that they used to detect only part of the data actually perfectly good enough for faithful reconstruction or faithful classification, whatever it is. Whereas compressive sensing tells you that you don't need to acquire an entire set of samples. We acquire only those samples that are actually critical. So what it tells you, right at the data collection stage, you impose a compression. Hence the name compressive sensing. So compressively we sense the data. So in this CT application, what is it that we are doing? Compressively, basically, we are acquiring the samples, except projections. So as a result, patient is not given entire dose. Only part of the dosage is given to the patient. At the same time, we can ensure that we can have the reconstruction of faithful quality. Okay, this is one application. One application where sparse device ideas can be deployed. So, under the question, before I proceed further. Yeah, please. Is there any internet chance to get a something? After I see, I think it's very conductions here. It's a between across samples. So, for a given set of samples, I calculate this set. Okay, we do not calculate explanation. I can speak a calculation. So, I can consider this part. For a given pattern, if you solve the calculation problem, you basically get a best subset of m samples. So, any other question? Okay. These are a question with some numerical results here. So, these are for different sampling rates. This is the sample rate is 10% here. These entries in the table actually currently reconstruction formulations. Okay. So the next problem is basically a line problem, which is about limited view tomography. So what I considered in the earlier problem, out of 1000 days, I tried to basically pick the best 100. Now the question is slightly different here. Slightly different in the sense that, see, this is corresponding to one angle, this is corresponding to another angle, like this. Suppose I say that I want to basically consider that, imagine that we have basically 100 angles. Okay. Suppose you say that I want to take best 10 angles. Okay, but within the angle, I consider all axes. So this is not limited. So here, the optimization is what with a simple difference. Out of 100, pick the best element. Okay, so this is limited with tomography. So if you put it in the matrix down here, in the table of optimization problem, you end up getting a kind of optimization problem where the possesses some block structure. Okay. So this is better having a block structure because look at the object is what. If you look at the way actually consider the optimization problem, there is a block structure. Look at this. See, you have a block structure here, right? So now requirement is one here, instead of all angles, basically you pick the data corresponding to some of the angles. Which means either you have to retain this block or you have to do it out. Okay, so this leads to basically what? An optimization problem where the solution has to be obtained with a certain block structure. Yeah. So this matrix actually possesses some block structure here. So you have to solve for the having certain block structure here. So this is basically what compressive sensing problem where we have to find the solution possessing certain blocks. Okay, so block based sample kind of deployed here to find the solution in this stuff wherein we retain the block structure. Okay. So there is something called adaptive compressive sensing. Some time back I made a mention of this. So adaptive compressive sensing is what based on medical imaging where the person undergoes particular test repeatedly. So after the patient undergoes the test first time, so image or the signal actually gives you some information about the problem. Like for example, because of the abnormality in the other image. So that abnormality actually gives you some information about the support. Right? Already you know, okay, this is the location where the abnormality is present. So when the patient undergoes scanning next time, that information is given. Okay, this is what we call adaptive compressive sensing. So here again, same matrix equation again, the way actually we generated same matrix equation is same here. The only difference is we actually trying to incorporate adaptive information. So that is one thing. Second thing, what happens in general in medical company, especially the matrix that is formulated is very bad at one time. Very bad in the sense that in comparison to probably something like I made a mention of this. Coherence parameter is something that gives you random. The matrix has very small coherence. It has actually better behavior in computation. But unfortunately, the matrix that you get in tomography have very bad behavior. So as a result, what happens? You run into problem. When you execute the algorithm, you face actually many numerical issues. So because of that, people actually try to propose optimization problem where the target function is different. Like for example, all these are actually great examples. So we consider unknown limitation. So in place of unknown limitation, researchers actually started considering some non-convex functions. So non-convex function would accommodate the bad behavior of this bad behavior of this matrix compared to convex function connection. So one such a non-convex function is something like this. This is non-convex function here. This function is defined like this. So even if this matrix is very, very extremely bad, okay, this function actually takes care of the bad behavior of the matrix. I'm not providing all details here. So these non-convex functions are shown to actually provide better reconstructions in applications later. Okay, these are actually reconstruction results with this particular cost function. This is my cost function. As opposed to one norm, or a weighted one norm here, we consider the cost function which is given by this particular function. Okay, when you, with respect to this cost function, is obtain the solution of this matrix equation, what you get is you get the reconstruction of this problem. You see here, I consider only 21 angular samples. 21 angular samples, these are all actually popular reconstruction methods. Popular reconstruction method, you see, FPP is the central reconstruction method. Very popular method in tomography. This is the classical element chart. I talked about it in the beginning. This is the transformation here. These are popular methods here. But compared to all these methods, the optimization problem where the cost function is taken like this is providing actual reconstruction of the video. So I consider basically same number of projections here. Same number of projections here, but with different cost functions. So when the weights are actually tuned properly here, when the weights are tuned properly, this particular method actually provides superior reconstruction. See here we have same set of projections. Same set of projection, but when you mathematically convert the problem, or when you mathematically convert the cost function, you can basically have the reconstruction of the video. Basically take more number of predictions. See, for example, in order to use this method, I need large number of samples. Right? Whereas you see, 21 samples here, this method is actually giving very good prediction. Almost the same as the original idea. But what is that is incorporated into the process of prior information. So prior information is I know that there is some problem here. Suppose we have to use the information from the previous scan. That there is a problem in this particular question. So with that, when that information is incorporated into the problem, so this is actually something corresponding to background information. I have information, reduced that from the previous image. I made use of that information in this optimization problem. So when I solve things, I have basically the reconstruction of the loop. So these are actually yes. So this is again sensing problem. Sensing problem in the sense that if I have real information about the signal that is to be reconstructed. Okay, I can incorporate that information into the application. So as a result, what I do now, I can use data of very small size. Okay. So this is actually another sensing problem. See here, I consider abdomen image here. At a given set of projections here, this method is actually going to be a reconstruction of superior quality. Some of the results are not here. So any question? So I talked about methods where actually smart stick can be used for learning purpose, like for example, dictionary learning that we have. You can make it up dictionary learning for classification. So this is that. In this next part, I started talking about the application where you see the role of sensing. state and basically imposing the compression state. Okay, so the sparsity based idea can be used for sensing as well. Compressor sensing the data compressing. This is another application. This is a collaboration. So we all know this. So what happens? The patient is analyzed in one place. Okay, the expertise is another place. So you have got samples from the patient, transfer those samples to the place where expertise is available. Then expert will get to see the sample. Then based on that, expert actually come up with his decision. Okay, this is the conventional architecture. So what is done here? All samples are acquired from the patient. All samples are transmitted to the place where expertise is available. Then expert says. So this architecture is actually code to all these problems. High sample rate. We are mapping all samples and all those samples are sent to the patient. High standard filter. Better transmission and etc. samples. So this method is basically for code to all these problems. Instead, we have a methodology like this. What you do at the patient here, you basically pick those samples that are resident. Only those samples that are relevant. So compressively, basically, we acquire samples from the patient here. Now, right at the patient here, you check if everything is fine with the patient. Or if some abnormality is there. If abnormality is there, what you transfer those samples to the place where expected. Okay, now samples are actually sent to the diagnostic center. But at the diagnostic center, expert has only few set of samples, not entire set of samples. So expert won't be able to make out anything from those samples. So what is it that we have to do here? We have to undo the experiment. So from the part of the sample, we have to get a risk apply a full set of samples. Then next the expert can make out something. So this whole thing, suppose we have this architecture. Okay, this architecture actually provides three advantages. Reduce the acquisition rate. Obviously, we are picking only few set of samples, right? The second thing is reduce the transmission bandwidth and low power consumption. So these are the advantages provided in this architecture. This is very actually demonstrates. The first problem is, as I told you have to pick only part of the samples, right? Which is subset of samples. This is obvious question. So it's a typical mathematical problem. Okay, suppose you succeed in addressing this problem. The second question is that it comes to you, right at the patient end, we have to be able to analyze the data. You analyze the data and say if everything is fine and if some abnormality is there. But why is that? I have only part of this. I don't have that. Let's say that we have one of this. So, if we do one of the samples, we have to be able to analyze data. What is the way to do that analysis? Right? This is the second question. The third question is that suppose you succeed in addressing this also. Then you transfer three samples. Now at the receiver again, we have to transfer the information. In the sense that from one of the samples, we have to be able to generate the second sample. Right? So otherwise, expert can't say anything about the problem. Now what is the way to basically do all this? What is the way to execute all these steps? Right? So this is where actually the underlying computation of the signals will come to receiving a very different. Okay, so let's see that. With this I start with the presentation. So we work on these problems. Look at the normal signals. They have some behaviors, some nice properties like approximately the behavior in the periodic signals. Right? Look at the abnormal signals again. This is abnormal signal of one type, abnormal signal of another type, abnormal signal of other type, third type. So these signals have certain properties, these signals have certain properties, these signals have certain properties. So what we try to do here, we try to analyze this. So this has all normal signals actually possess certain nice statistical properties in the sense that they have a listed non-negative property, statistical property. We estimate the associated Harris experiment. For all normal signals, the Harris experiment values lie in a small interval. Okay, that gives you hand-to-hand properties of the signal. Similarly, for signals of this type, or for signals possessing abnormality of this type, the corresponding Harris experiment values actually lie in another interval. Okay, so the Harris experiment values actually provide us with hand-to-hand properties of the underlying signals. You see, so based on non-member, we cannot see anything about the property services. We cannot arrive at a conclusion. There is another property that is naturally within the these signals. Okay, that property is not. If you look at the autocorrelation coefficient of these signals, that can be complicated. Something actually happens. So what we try to do, we try to catch one of these properties. We actually look at the values of those parameters for all signals. For abnormal signals, for normal signals, those values actually are in something like. For abnormal signals of another type, those signals actually are in that. Okay, those properties actually will be exploited. Not only this signal, normal signal, if you become more efficient, you will domain. Because of its natural property, it gets sparse representation. So certain things are naturally happening in the signals. And we try to actually make use of all those properties in order to basically against all these issues. We showed that when those properties are properly exploited, we showed that one-fourth of the sample, 40% of the samples, we can basically catch one of the properties of the signals. Okay, with those 40% of the samples, basically we can compare the aspects for it. So you see here, this partially based again is actually compared. Okay, so from the patient, you pick basically only 40% of the samples. So for normal ECG signals, you take only 40% of the samples. And using those samples, basically we estimate hash rate. See, for estimating hash rate, we showed that we don't require all samples. So as I told you already, you compare H values, hash rate values, you compare the autocorrelation coefficient values, you get the range. Okay, the range actually gives you something about the properties of the underlying signal. Okay, but for computing those parameters, you don't need actually entire signal samples. Right? So now what you can do is that you can basically compute the values. See, imagine that you are considering only 40% of the samples in the patient. Okay, after acquiring those samples only, you compute the values. You compute the values and check if the signal is not abnormal. If the signal happens to be abnormal, you transmit. Okay, transmit to the place where expert is available. Now at the receiver end, what you do from those 40% of the sample, you can basically observe everything. See here, we use the compression in this area. You observe everything, you can generate signal of light. Okay. The expert actually can see that. So all these things actually can be realized by interpreting the properties of the underlying signal and then make use of sparsity based values. You see, setting now. See, I'm not taking the whole value to the patient. I'm taking only 40% of the sample. Okay, so this way, the sparsity based idea can be interpreted in sample real time applications. And not in interpreted way. So anyway, I avoid all mathematical details here. Just avoid handwriting statements mostly. Very beautiful mathematics behind all these things. Okay. So with this, I'm done my presentation. Thank you for having the attention. Any questions?
Thank you, so for your talk and enlightening us more about sparsity-based learning. I will now request Professor Linga sir to give the thank you.
Thank you.